In this tutorial, you will learn how to design and build your own board using Altium Designer. Even if you have never designed any board before, by the end of this video, you will be holding your own ESP32 board. You will learn how to draw schematic, create libraries, do PCB layout, order your board, solder components, test it, and then write and upload your software. Let's get started. Open Altium Designer, go to File, New Project, Local Projects, find the directory where you would like to save it, select folder, and I'm going to name this project, I'm going to name it ESP32 with USB-C. Create. Now right click, add schematic, add also PCB, and we would like to also include schematic symbol library and also right click, add, and PCB library. These are all the files we need. Now right click, save our schematic. I'm going to save it inside of our project directory and I'm going to call it ESP32 with USB-C. Copy this name, save. Now right click on PCB, save as. Just paste the name. I'm going to add PCB version 1 issue 1, save. Save PCB library as PCB lib, and same for schematic symbol library, simply just save it as schlib. Save. Okay, save our project, go to Google and search for ESP32. Okay, this is the website where we would like to go and find development kits, find the module which we would like to use in our project. This one, ESP32 S3 Mini. So open this user guide and when you scroll down, there are links to all the documents what we need. So I'm going to open this datasheet of the module and notice they have two. This one is with external antenna, but this is the one what we need, what we would like to use. I'm going to copy the name of this module with PCB antenna, go to DigiKey, and I'm going to find the module in DigiKey. So paste the name of the module here, search. Here it is. And this is our module. Copy DigiKey part number. Go inside of our library. This is very important. Panels, manufacture part search. You have to be in the schematic symbol library, okay? Schematic symbol library has to be open in background behind this manufacture part search. Find DigiKey here and we are going to simply just press right click and import information about the ESP32 module from DigiKey inside of our schematic symbol library. Go to schematic library panel, delete the default component. This is the empty component which is always there when you create a new symbol library, and this is the module. This is our symbol what we have created. We still need to create the symbol itself. We need to draw it. So I'm going to download datasheet, and inside of our project directory I'm going to create new folder. I'm going to call it dots, and I'm going to copy datasheet here. So we have all the documents what we need for the projects in one place. I'm going to open it, make it a little bit smaller, and we are going to use a very cool trick how to create a symbol with many pins. So I'm going to adjust this view a little bit, go to pin description, and basically we are going to copy all the pins which are here in datasheet. We are going to copy them to Excel spreadsheet. I'm going to open it, and then very simply we will import these pin descriptions into Altium, so we don't have to write everything manually. In this first column, I'm going to put pin numbers. Okay, pin number 1 and 2 are ground, so I'm going to put ground here, and I'm going to use _1, and for pin number 2, I'm going to use _2, because I like to have different pin names. I don't like to have same names for multiple pins. Pin number 3 is power, and this one, I'm going to use a trick here, hold Alt down to select all the pin names like this, paste them here, and we are going to make a little adjustments. This bold pin name is the default function after reset, and I would like to move it at the beginning of the pin names. So I'm going to delete it from the end and just paste it here at the beginning, and do it also for the second one. So simply select the GPIO 1, because this is the default function of the pin after reset, and put it at the beginning. I'm not going to do it in the video for everything. You can just do it by yourself, okay, because it just would take too long. I would like to just show you what you need to adjust. This is another thing what we need to adjust, because this belongs to pin number 14. So I'm going to place it here, and this is supposed to be pin number 15. So I'm going to move it here, and again, this is supposed to be part of the pin number 15. So copy, place it here. Same for all the other lines, okay? Double check all the lines. If there is something like this, correct it. Okay, I'm not going to do it again in the video because it takes a lot of time. Actually, I created whole file a little bit later. You can just download the file. Another adjustment, replace the comma and space with slash, because in pin names you would like to use slash. It's very well visible. Okay, so this is basically, these are all the adjustments what you may need, and once you finish it, it will look like this. Okay, so these are all the names which I finished, and this is how it should look. I'm going to adjust this pin names column so we can see all the pin names. I'm going to save the file. When you download the whole project, I will attach a link to GitHub under this video, so you can download whole project including this file, so you don't have to write this file by yourself, and then you can simply import this. You can simply open it and import these pin names into Altium. You will see how to do it in later. This is the file, okay. Now notice all the ground pins which are here, many ground pins. If I go down here, you can see there is basically like only 45 pins in the table, but if I zoom in on the footprint, there are many ground pins, and some of them are actually additional. Some of them are here in this row, but some of them are actually in the corners and also in the middle of the footprint. So we need to add all these ground pins into our table. Now, go to Altium, Tools, Symbol Wizard, and we are going to create the symbol. So first we would like to know how many pins are there, 73. So I'm going to put here 73. And we would like to have all the pins just in one row. We will be moving them around anyway, so it doesn't really matter. Now I'm going to copy all the pin names. Simply just select them, shift, hold down, left click, and place them here. So this is a very simple way how you can create so many pins. You can basically import them from datasheet. I'm going to change the electrical type to passive for all the pins, and we can place the symbol into our library. Perfect. Cool. If you would like to zoom in, zoom out, by default you need to hold Control and use mouse wheel, but I'm going to disable the Control because I find it much easier just use the mouse wheel. And to select objects, you can use this blue rectangle, or you can use green rectangle. One you draw from top left corner, the other one from bottom right corner. Difference is, in one case you select everything inside of the rectangle, in the other case you select everything inside and touching the rectangle. Use X and Y to flip or mirror the selected objects. X and Y on your keyboard, okay? And I'm going to make the pins a little bit shorter because they are quite long. So I'm going to use this filter. I would like to work only with pins. Select all the pins and simply make them shorter, 200 mils. It looks okay. Don't forget to put the filter back so you can work with all the objects. And I'm going to move these individual pins. Use spacebar to rotate the pins, put them up here. Now I would like to move it a little bit. Use X and Y to mirror or flip and put them like here. Okay, I'm going to move these pins up here. You can do it exactly the same way, so your symbol looks exactly same as the one what I'm drawing. You can simply just use the grid as a reference. You can see where I put the pins and how I draw them. I'm going to select all these pins, move it a little bit down. And also I would like to move some of the pins on the right side of the symbol. So I'm going to select these. Again, use X and Y on your keyboard and place them like here. Move also these pins. Put them up here. Okay. Make this yellow box smaller. And yeah, it was not so difficult, see? I would like to make it a little bit nicer, so place text inside of our symbol, because this is the most important symbol in our schematic, and I would like everyone to know that this is ESP32 S3 mini module. Make it a little bit bigger and move it maybe like, I don't know, like this. Cool. Save our library. Add designator, U question mark, and add comment. I'm going to put here the name of the component. So these two are visible in schematic. And also I'm going to add parameter. I'm going to call this LCSC par number. And we will use this parameter to put here par number from LCSC company. If I go on their website, you will see this is a company which is selling parts, and these parts can be used by JLC PCB. So when you will be building your PCB in JLC PCB company, they can use LCSC parts and fit them on your board. So I'm double checking this LCSC part number. So we can add this number into our symbol, and then JLC PCB will know, oh, okay, this is the part which we should fit on your board. I will make it favorite so we can see it in every symbol what we will create in future, and save the library. We created schematic symbol library with one component ESP32 with designator U question mark and comment ESP32 S3 mini. There are some parameters which we imported from DigiKey. We don't have to write this manufacturer part number manually. It was imported. And that's it. Be sure our schematic symbol library is saved. Go into our schematic, panels, components. Here in this list, select our schematic symbol library and drag and drop the symbol what we have created into our schematic. Here you can see this is the designator, this is the comment, and this is unusual, this gray background behind the pin names. It's like special feature of Altium, and we would like to remove it because we are not going to use it. So go back into schematic symbol library, select a pin with this complicated pin name and just remove these functions. Okay, select pin and remove all the functions, just press cross to remove it. I'm not going to do everything in the video. I'm going to stop recording and do it because it takes a long time, but remove it for all the pins. I'm finishing removing, and now all the pins are corrected. Save schematic symbol library, go back into our schematic, delete this symbol, just select it and delete, and drag and drop the new one. Now you can see the gray background is gone, so it looks perfect. This is exactly what we would like to have. Save our schematic, and now maybe make it a little bit bigger because it's quite small, so I'm going to use A2 and I'm going to move it maybe like here. Okay, I would like to put some information into this table, so I'm going to place text here and here, and I'm going to change this. I'm going to put here the project name ESP32 with USB-C, and here I would like to add some information about my company, so you can put here information or copyright about your company, in my case designed by FEDVEL. Okay, and also I would like to put big title on the top of this schematic page, so place text and again put here name of our project ESP32 with USB-C, and make it bigger, so when you open your schematic or when you print your schematic, you immediately see, oh, this is my schematic from ESP32 project. Super useful. Place it maybe like this. Okay. Save schematic. I always keep saving everything just in case. Now go back to ESP32 website and open reference schematic. We would like to see what other components we need to connect to our ESP32 module. So this is the module, and we need to connect there, for example, this 100 nanofarad capacitor. Go to DigiKey and search for 0.1 microfarad 0402. Click on these ceramic capacitors, and we are going to use Samsung capacitors, X7R 50 volts in stock. Apply, and let's use this first one. Copy the manufacturer part number, go to LCSC website and double check if they have it. So I'm going to search for this capacitor. They have it. Perfect. So we can copy DigiKey part number and go back to Altium. Very important, go inside of our schematic symbol library and click on panels, manufacturer part search, right click, paste, enter, and find the capacitor. In DigiKey, do right click, import. Now we have two components in our schematic symbol library. We imported all the parameters from DigiKey automatically, so we don't have to write them. And we are going to draw the symbol, place pin, press Tab to edit parameters of this pin, and then just click on this pause button, press spacebar to rotate, and place the pins inside of our schematic symbol library. Be sure this white end of the pin is facing out of the symbol, because these are the electrical ends of the pins. And change the grid. Just press G on your keyboard, G on your keyboard, to make it smaller. And we are going to draw a line. Press tab. Be sure you are drawing blue small line, and just draw it like this. You can watch the position of my cursor. Okay, down here you can see the position, so you can draw it exactly the same way as I do it here in the video. It's very simple to draw the schematic symbol of capacitor. Do it like this. Okay, now press G, put the grid back to 100 mil. This is very important because you always would like to have these pins placed on 100 mil grid. Otherwise, you will have a lot of problems when you will be creating schematic. Change the designator to C ? And comment is going to be 100 nanofarad, 50 volts. I'm going to copy description from the DigiKey website because, you know, this is nice short description, so I'm just going to put it here. And we would like to also copy the name of the new parameter, this LCSC part number. We would like to copy it and place it as a new parameter into our capacitor. And also we would like to copy the LCSC part number from their website. So I'm going to copy it for our capacitor. Just copy and paste it here. Okay, save. This is very important. Save our library. Go back to our schematic components and drag and drop this new capacitor. Press spacebar to rotate it, and I can see there is comma missing in this comment. So go back to our schematic symbol library, add comma. Now save the library, and this is very important. Right click on the symbol, update schematic, because we already have this symbol in our schematic. We need to update it there. So now you can see we have the correct symbol in our schematic, updated symbol. Go back to reference schematic and let's have a look what else we need to add. For example, this 10 microfarad capacitor. So I'm going to search in DigiKey for 10 microfarad 0402. And let's click here, ceramic capacitors. Again, I'm going to use Samsung 10 volt in stock, apply. There are only two, and this one is not for new design, so I'm going to use this one. Copy the manufacturer part number. We would like to double check if they have it in LCSC, so paste it here and search. Okay, they have it. This is the capacitor, perfect. So go to DigiKey, copy DigiKey part number. Now go to Altium, very important. Go into schematic symbol library, panels, manufacturer part search, right click, paste, enter. We are going to import all the parameters from DigiKey. So find the DigiKey box here. Now right click and import. Close this. Go to schematic library tab. We have new component with all the parameters from DigiKey imported, and we don't have to draw the symbol because we can simply copy the symbol what we have created for the other capacitor, and we can simply just paste it into this new capacitor. Okay, double check the pin numbers. So this is pin number 1, pin number 2, perfect. update the designator to C question mark, and also update the comment. I'm going to put here 10 microfarad, 10 volts. Go to DigiKey, copy this short, nice description, paste it here. And what else is missing? We need to, or we would like to copy this LCSC part number name and create new parameter and paste the name here. Oops. Okay. Go to LCSC website, copy the part number and paste it here. And it's done. New capacitor very quickly created. Save schematic symbol library, go back into our schematic and simply drag and drop this new capacitor. Press spacebar to rotate and place it like this. Let's go back to our schematic. We created this. It's connected to 3.3 volt power. We are not going to create the 0 ohm resistor, so we can directly connect these capacitors and use this wire drawing tool, connect them to 3.3 volt pin. Place power port, and we would like to rename this to plus 3V3. We would like to use bar and rotate this. This is going to be our power. And we would like to also place ground. You can just connect it like this, put it on the top of the pin and just move it. Hide the name of the ground. We can copy it, paste it and connect also to this other capacitor. Okay, save our project. Next, we would like to connect all the ground pins to ground. So let's do it. Zoom in. All the ground pins are here. So it's going to be super simple. Just connect everything together. And to speed up this process, we can simply copy and paste these short tracks. Copy and paste this super useful feature. Okay, almost done. Okay, I can delete this one. And copy the ground symbol and paste it. Save. Next, we are going to name all the nets. We are going to connect all the pins on our symbol. So we need to draw these connection wires from each pin on our symbol. And again, we will use the copy and paste feature to make it a little bit faster. Okay, paste, paste. This is just one line, so I can draw it. And paste also here. Paste. Almost finished. These are ground, so I'm going to delete this. I will move this up and okay. I will connect these two ground pins so we don't forget about this. Okay. Now we are going to name these nets. So place net label, press tab, and I'm going to put here GPIO 0. And we do it this way because then Altium will automatically increment the net name. See? And watch if you are correctly placing these net labels. Okay, GPIO 20, you can see it here. And now be careful, okay? 21, this one is 26. So 26. Next one is 33, 34, and let's continue. Okay, 46, 47, 48. We don't need this, we can delete them. And this one is called chip PU, so I'm going to place net label, and manually I'm going to name it like this. Okay. U0TX and U0RX, so I'm going to copy this and place it correctly, okay? Don't make mistake, this is very important. Double check the pin name and place the net label correctly. This one is the RX, the other one is TX. Okay, perfect. What else? Everything else seems to be just GPIOs. So don't forget to save your project. Now another capacitor, 1 microfarad. Search in DigiKey. We are going to use Samsung. 1 microfarad. 0402. 35 volts in stock. Apply. There is only one, so I'm going to copy this manufacturer part number. Let's have a look inside of LCSC. They have it. Okay, we will use this part number later. So copy DigiKey part number, go to Altium, go inside of our schematic symbol library, panels, manufacturer part search, paste, enter, find DigiKey, right click, import, close, schematic library, copy existing symbol, so we don't have to draw it, go inside of our new symbol, paste it here, double check the pin numbers, and change the designator, put here the comment, go to DigiKey, copy description, paste it here, copy the LCSC part number parameter, okay, go to LCSC, copy the number and paste it here. Save the schematic symbol library, go to our schematic, go to libraries, and I'm going to adjust this column so we can very nicely see which capacitor is which. So I'm going to enable this command and put it up. Watch what is going to happen. See, now I can very nicely see which capacitor is which and place it somewhere here, okay? We are going to build here or create here circuit, very small circuit around this 1 microfarad capacitor. So just place it here. go back to reference schematic. We also need this 10K resistor. So for very first time we are going to look for a resistor component, and we will need to create also a symbol. So I'm going to use this manufacturer Yageo, plus minus 1%, 10K in stock, apply, and we can use automotive. Let's use this one. Double check if they have this one also in LCSC, so they can fit it when they will be building our boards. Okay, they have it, perfect. Go back to DigiKey, copy DigiKey part number. Open library, manufacture part search. Import the resistor from DigiKey, here it is. So right click, import. Okay, and we are going to draw this symbol. So place a pin, press tab, or adjust the parameters. So designator 1, name 1. I'm going to leave pin length 100. Okay, hide the designator and name. Be sure the white end of the pin is facing out of the symbol. Now, I'm going to add grid, so it's easy to draw this symbol. Press G, change the grid to 25 mils, and watch how I'm going to draw it. Watch where I'm going to place the cursor. Press spacebar to draw this way under an angle, and draw resistor symbol. Okay, perfect. Press G, go back to 100 mils. And finish the symbol. Super easy, very quick way how you can draw your own symbols. A little bit later we will also import some symbols, you will see. So this was just to show you how you can create your own symbols from scratch, okay? Because sometimes you will not be able to find symbols for some of the components. You need to know how to create them by yourself. Go back to LCSC, copy the LCSC part number, almost. Resistor is almost finished, so paste it here and save the library. Go to our project, go to our schematic and place the resistor. Okay, press spacebar to rotate. And let's have a look into our schematic, how to connect it. Okay, so I'm going to search where this is connected. It goes also somewhere here, and then to this button, to the resistor and capacitor, to header, and also to our chip. Okay, maybe we should also create this switch. So I'm going to find a button which we could use. It's called tactile switches. I'm going to use this C and K surface mount, and a very standard size is like this one, 6 by 6 millimeters. Again, in stock, don't forget. And you can choose different colors, different sizes. I will use this gray one. I'm going to double check if they have it in LCSC. Maybe delete this space. They don't have them in stock, but it's okay. Don't worry about this, okay? You can always buy them from different supplier. I'm still going to use it, so copy digikey part number. Go back to our library. Search. Find digikey. Right click, import. And this time we are going to learn how to reuse the symbol and footprint. So I'm going to download this symbol and footprint. Inside of our project, I'm going to create new directory, temporary directory. And here I'm going to save the symbol and footprint, which will be imported directly from this manufacturer part search. So we don't have to draw the symbol and footprint, we can easily copy it. Okay, so now this is the file what we have downloaded. Go inside, and we would like to unpack this PCB library and schematic library because that's what we need. And I'm going to name these, so later we can very easily find them rather than, you know, using name components blah blah blah. I'm going to call it the right name, and I'm going to open it. So simply just drag and drop the schematic symbol library into Altium, and there is one component. It is this switch. So select everything, copy it, go inside of our schematic symbol library, select our switch, and simply just paste the symbol from the file what we have downloaded. We can close this one, this downloaded library, and we can just finish our symbol. So change the designator. I'm going to call it SW question mark. Comment is going to be switch part number. Description, as always, I copy it from digikey. And then we need to add LCSC part number parameter. So let's do it. And also we need to find the number. Copy it and paste it here. Okay. Save everything. Go back to our schematic. Now in components, select our library, drag and drop the switch, and now we can connect it. Okay, so I will move these things a little bit around so it looks nicer. Open schematic and double check how it is connected. This one is not fitted, so we are not going to place there the capacitor, the other one. We just need to connect it like this. Okay. Okay. And we need to connect ground to the other pins and ground to the capacitor. So this is connected to ground. I'm going to copy the symbol and paste it. Very often if I have something already in schematic, I just copy and paste it so I don't make mistakes when creating something new. And also we need to connect the resistor to the 3.3 volts. Okay, it's the same 3.3 volts where the capacitors are connected. So I'm going to copy, paste it here. Okay. And what else? We need to connect it to the ESP32 module. So copy this pin name or net name and paste it here. Again, I use copy and paste so I don't make mistake when rewriting this net name manually. And save everything. This is the, we have to check which button we just created, so that's what I'm looking for. So it's on pin number 45. And I'm going to open this PDF, and here are the buttons. I just need to double check the layout. So which one is pin number 45 on the module? This one. Okay, you can see this is the pin number 45 and it is connected to which one? Which button? This one. So how this one is called? It's the reset button. Okay, so I'm going to copy this text and I will make it smaller, and I'm going to change it to reset button. Okay, so everyone knows this is the reset button. Save our schematic. Go back to our reference schematic, and we are going to add this second button. And there is this 100 nanofarad capacitor, not connected capacitor. What I'm going to do, I'm going to do this. I'm going to copy this existing circuit, paste it down here, maybe delete this. Delete this 1 microfarad capacitor. We would like to put there this 100 nanofarad capacitor. Just copy it. And don't forget, this one is not fitted, not connected. NC means not connected. So I'm going to place text over this capacitor. And on the text, I'm going to put a node, NF, not fitted. I will make it a little bit bigger and red. Change the grid, press G on your keyboard, make it smaller. So we can very nicely place it over the capacitor, put the grid back to 100 mils, and now we will know this capacitor is not fitted. I'm going to copy also this description of this sub-circuit, so everyone knows this is what button it is. Boot button. And we will use this also as a user button. So I'm going to put here a note like boot/user button. I'm going to delete this. Don't forget to save your schematic. And we are going to connect the button. So go to reference schematic, double check where it is connected. GPIO 0. Where everywhere is GPIO 0 connected? It's connected to the module, it's connected to the header, then this circuit, and to our button. And this is quite important signal. So what I'm going to do, I'm going to connect this GPIO 0 a little bit differently, and I will need 27 ohm resistor for this. So first I'm going to create it, 27 ohm 0402. We would like to use Yakeo 27 plus minus 1% in stock. You will see a little bit later how I would like to connect it. So let's use this one. Double check if they have it in LCSC. Search. Okay, they have it. Perfect. Now copy DigiKey part number, and we are going to create it in our library. So go to library, panels, manufacture part search, paste the 27 ohm resistor, find it, and right click import. It's going to be very quick because we already have resistor symbol, so we can just copy it from here and paste it into our new 27 ohm resistor. Okay, double check the pin numbers and update designator is going to be R question mark, update the comment 27R, copy the description, and also add the LCSC part number parameter. Okay, go to LCSC website, copy the LCSC part number, and the resistor is finished. Okay, don't forget to save the library. Go to our schematic, drag and drop the 27 ohm resistor into our schematic, and this is how we are going to connect it. Watch. First, make it a little bit nicer. We need two of them, and we are going to split this GPIO 0 signal through these two resistors. And we are going to split it because this may help with improving the signal quality, and also in future, if you would like to disconnect part of this circuit, you can very easily just unfit one of these resistors. That's why we did it. Let's have a look where we need to connect it. So again, GPIO 0 is connected to the headers or the connectors, and to this circuit, and to this button. Okay, so what I'm going to do, I'm going to place these net labels, and one of them I'm going to call con GPIO 0, and the other one I'm going to call what do you think? Button GPIO 0. Okay? And now we can simply just copy this and connect our button. Okay, and later we will connect the rest of the circuit. Don't forget to save your schematic. Go into our reference schematic, and what we are going to connect next? These USB connectors, and originally these are micro USB. Okay, if you have a look on the board, these are micro USB connectors, and we would like to make it better. We would like to use USB-C connectors. So search for these 99 Tech, and they have boards with USB-C headers. I'm going to find it. For example, this one. And we need to have a look how they connect these, okay? You can see these are the USB-C. And they have also schematic here. So if you are not sure how to connect something, you can find a similar reference schematic with the circuit, what you need, and you can double check how they connected it. So this is what we need to do. This is the USB-C circuit. Okay, I'm going to find the USB-C connector. That's the first thing what we need. And I'm going to use Molex connectors. There are many USB-C connectors. I would like to pick a specific one, which is quite simple to connect on our PCB. So that's what I'm doing right now. I'm searching for top mount, and only with 16 pins. not this one, not this one. Dual row. We don't want dual row. It's very hard to solder manually. Oh, this one looks like a good one. So I'm going to copy this part number. And let's have a look if they have it in DigiKey. In stock, okay. We can also double check if they have it in LCSC, but from my experience, yeah, they don't really have like these Molex headers, but it's okay. We are going to use it anyway. So copy DigiKey part number. And create new USB-C symbol in our library. So import all the parameters from DigiKey, and we can also use maybe later this footprint. So I'm going to save libraries into our project. This is the file what we have downloaded. I'm going to unpack the schematic symbol and PCB library for the USB-C connector. I'm going to copy the name of the connector, and I'm going to rename the libraries. So later we can very easily find which file or which library belongs to what component. Okay, I can delete this, we don't need this. Okay, perfect. And let's have a look on the symbol. This symbol is not like the best one. That's not really what I would like to use, so I'm going to close this. And maybe we can create the symbol by ourselves. Open datasheet, and this is going to help us to draw the symbol. Let's have a look at what pins we need to create in our schematic symbol. So I'm going to make this datasheet a little bit smaller because we would like to see it when we will be drawing the symbol. Maybe like this. Okay. These are all the pins we need to create. I will make this a little bit bigger and place pin. Where is the zero position? Escape. I'm going to find it again. Place pin. Okay, so here is 0, 0. Now press tab. And I'm going to put here A1 and A1. Make the pin 400 mils and place them. How many do we need? Up to A9 maybe. Okay. And now do same for B. So B1. Place B pins here. Maybe like this. And then don't worry, we will adjust the pin names. We also need these ground pins, so I'm going to call it like S1, like shield, and we need 4 of them. Okay. Save everything, and let's make it nicer. A1, A4, B8, A5. You don't have to always order the pins as they are on footprint, but in this case it's very nice to see how the pins need to be then connected also in layout. That's why I'm using exactly the same order. And also you can very easily visually then compare that you have all the pins and they are correctly named. Okay, I will move it a little bit. A1, B12, so I'm going to change the designator to A1, B12. This one is A4, B9. Okay. Also this one. And also update this one. Perfect. We are going to name the pins. So when we will be drawing schematic, we can very nicely see where these pins are connected. For example, this one, you can see it's supposed to be connected to ground. So I'm going to call it ground A1, B12. This one needs to be connected to VBus. So VBus A4, B9. This one is SBU2. Next is CC1, B7. This one is connected to DN2. So this is the negative, second negative signal. This is the first positive signal. This is the first negative signal, and this is the second positive signal. There are two differential pairs connected to this header because, or there are pins for two of them, because you can connect USB-C in, you can rotate the connector. When you are connecting cable, you can connect it both ways. That's why there are two of them. This one is ground again. Rename also all the shield pins. We can do it all at once. Select more pins and do it like this, okay? It's much faster. So this is the shield _4. Perfect. Now double check if you named everything correctly. It's very important you don't make mistakes. We can continue in Altium. We can make this nice. So I'm going to draw this yellow box. We would like to move it to back so we can see the pin names. Okay, and let's put some graphics inside of this symbol so everyone can see, oh, this is USB-C connector. So draw it like this. Put there these lines and ovals, and so it looks a little bit like USB-C. Play with it, make it nicer. Okay, maybe like this. I like it a lot. Let's put USB-C text here. Press G, change the grid, so you can place it very nicely into middle. Okay, now press G. Don't forget, go back to 100 mil grid and save the symbol. Update the designator, use J ? As a comment, I'm going to use the part number. Very often I use part number in comments because then if someone is looking at your schematic, they can very easily find the specific component. Okay. Copy the description from DigiKey part or DigiKey website, and don't forget to add the LCSC parameter. I'm going to copy it from their website Okay, and it's done. Don't forget to save. And now we can place it into our schematic. So go into our library, drag and drop it. Cool. See? So complicated symbol and you created it very easily. Well done. Now you know exactly how to create any kind of symbol what you will ever need in your projects. We need two of them, and I'm going to name them before we connect these. So the first one is going to be the USB-C connector 1, and the other one is going to be very hard to guess. It's going to be USB-C connector 2. Okay, I'm just going to change it. Perfect. Save. Go to reference schematic. We would like to know how to connect this USB-C connector. We need to connect the V bus together, ground pins together, and we would like to connect also the USB pins. So this is going to be very simple. First, let's connect the USB pins, DN2, and DP1. We need to connect these two together with DN1 and DP2 pins. This is not the most optimal for layout, but for this very simple board, it is just perfectly fine. So we can connect these together. Then connect all the shield pins together and the ground pins of the connector. So this one, this is also ground pin, and these are the shield pins. And connect the V bus pins together, like this. Okay, and okay. I'm going to copy the ground symbol, paste it here. We would like to name the nets. This one is going to be connector 1 underscore USB underscore N, and the other one is going to be underscore P. Okay. Be sure you correctly name these nets, it's very important. And we can finish this power. So maybe I will copy the power port and then just rename it. So from this plus 3V3, I'm going to change it to plus 5V underscore V bus 1. And also we would like to add this 100 nanofarad capacitor. I'm going to copy it together with the ground connection. When we will be doing PCB layout, we would like to place this capacitor close to the connector. So we place it in the schematic, we place it close to the pin. This is a reminder that in the PCB layout we would like to have it close to the connector. Okay, save it. We would like to connect the rest of the pins, these SBU and CC pins. Let's have a look how they are connected. CC pins are connected through this 5.1K to ground, and SBU are not connected. I'm going to put there this not connected marker on the SBU pins, and I'm going to create 5.1K resistor. Okay, we would like to use same parameters what we usually use for resistors, so plus minus 1% in stock, 0402 automotive. I'm going to use this automotive one. I will double check if they have it in LCSC, so they can fit it. Okay, and we need to create the symbol. You know exactly how to do it. It's going to be simple because we already have resistor symbol ready. Now maybe you are asking why we have to create all these individual components. This is how it should be done for professional schematic. Because if you are designing boards with many components, having a symbol for each specific component is going to make it much easier to manage all the components on your board. That's why we are creating every single individual component on your board. It's almost finished. Just update this description, add this parameter, and then we can use it in our schematic. Okay, this is the last thing to paste here. Save it. Go to our schematic and place the resistors. These are connected to CC pins, very simple connection. And the other side of the resistor, do you remember where it is connected? You can double check in reference schematic. It's connected to ground. I'm going to copy the ground symbol and paste it here. Do it also for the second resistor. Okay. Don't forget to save your schematic. Next, we would like to add this protection. So I'm going to copy the exact name of the protection what they used here and search. Oh, they don't have it in DigiKey, so we can just find something else. I'm going to find this USB protection, ESD protection. It's for USB interface. Select it. What do they have? We can use this one. I'm going to copy it. They don't have it in LCSC, but it's okay. We can solder this manually later after our board arrives. And we need to create symbol for this protection. Import the parameters from DigiKey, and it doesn't have footprint and symbol. We need to draw it. This is going to be fun. So place pin. I'm curious if you could do this by yourself without actually watching this video, because by now you really should be able to create any kind of symbol. So you can try it by yourself if you like. Or you can follow this video and you can create a symbol like this. I'm going to use very small grid and draw it like this. Again, if you need help with drawing, just watch the position of my cursor and then you will know how I draw it exactly. I'm going to use this polygon, and this is maybe too big, so I'm going to make it smaller, and we would like to have it blue color, so I'm going to select blue. Okay, how it is going to look. Perfect, this is really nice. Do it also for this second one. Okay, cool, this was very quick. Don't forget to change the grid back to 100 mils, and also update the designator and comment, copy description, and add the parameter. If you would like to learn more about the reasons why really we are doing it this kind of like complicated way, have a look on our FEDVEL.com website. We have many online courses, and they explain how to do professional design, board design. We need to connect this protection to VBus and to the USB pins. So I'm going to just drag and drop it into our schematic. We need 3 of them. Okay, and simply connect these. So this is ESD protection. It means, for example, when someone is touching the cable or the connector, the ESD impulse will not go inside of your board and it will not damage the component connected to this connector. Okay, same circuit is also on the other connector, so we are going to draw it. I'm just kidding, we are going to copy it because that's much faster. See, super quick. Don't forget to rename the power. This is going to be VBus 2, and also the USB signal. These are going to be connector 2 USB signals. Okay, what next? Go to our reference schematic. They have this diode here. I'm going to, instead of the diode, I'm going to use a jumper. So I'm going to find a header for our board. And then through the jumper, we will simply select which of the connectors we would like to use to power our board. I would like to use a small one, pitch 1.27. Through hole, maybe this one. Okay, this looks like what we could use. I will double check if they have it in LCSC, but this is not really important because fitting through-hole components during board assembly may be unnecessarily expensive, so we can solder down this connector or header by ourselves to save a little bit of money. So even if they don't have it in LCSC, it's fine because we will fit this after we receive our boards. symbol is very simple. Just put there 3 pins. I'm going to change this to 1 and 200 mils. Now put here 3 pins, 1, 2, 3. Draw the yellow box. Move it back. Maybe make it a little bit bigger. And finish it. So designator is going to be J question mark, comment is the part number, description from DigiKey, and the LCSC part number is going to be from their website. Okay, almost done. Save the symbol and use it in our schematic. So instead of diode, we will use this jumper, and depends how we fit the cap on this jumper, we will power our board from the first USB connector or from the second one. So pin 1 and pin 3 are going to be connected to the USB connectors, and pin number 2 is going to be the main power for our board. Okay, copy this power port, place it on pin number 3, and copy this power port, place it on pin number 1, and in the middle is going to be 5 volts for our board. I'm going to rename this. Okay, save. And we still need the cap on this jumper, so I'm going to search for the cap. Where it is? Here. Okay. I will use Harwin in stock. 1.27 pitch. Height this one. Okay, let's have a look. I like the red one, so I'm going to use this one. And we are going to double check if they have it. Again, this is not important because we don't have to buy this from LCSC. Even if they don't have it, it's no problem. I just would like to see the number. And we can create it. And now you may be asking like, why we are creating this symbol in our schematic symbol library? Because this is not like real component. This even doesn't have any pins. So why do you think we are creating this symbol? Because we can include this cap in bill of materials. We are going to only draw the lines, okay? We don't need pins. We can include this in bill of materials. So always when we are building our board and when we are buying components for our board, we also buy these caps because they have to be placed on the board. If you forget to buy them, you can't really use the board, okay? They are part of the board. That's why we are creating this symbol and we are making this part of our schematic. Okay, very simple. We can save it. We need to change the designator, update the comment and description. Okay. And LCSC part number, copy, paste. Okay, go to schematic and place this cap close to the header. Okay, save our schematic. What is next? What do we need to do? We need to convert these 5 volts to 3.3 volts, and it is done here. Okay, so 5 volts converted to 3.3 volts, and we need this regulator. I'm going to find a regulator. This is how you can do it. So in products, integrated circuit, power management, voltage regulators, low dropout regulator, and I really would like to use one from well-known manufacturer, Texas Instruments. And maybe I would like to use similar footprint what they have on development kit, like this one. .5 amp and 3.3 volts. Okay, there is only one. We can use it. I'm going to double check if they have it in LCSC, because it would be good if they solder it down. Looks like they should have it, but only 11 pieces, so I'm not sure if they will have it when we will be building our boards, but it's okay, we can solder this manually. We are going to find it in this manufacturer part search, import the parameters and download the schematic symbol and the footprint, because it can save us some time. If there is footprint, we don't have to create this manually. Okay. This is the file what we have downloaded. Unpack the schematic library and PCB library. We would like to name these libraries, so I'm going to copy the part number and paste it here. Okay, now open the schematic symbol library, what we have downloaded. We can copy this symbol, paste it into our library, and we don't need the downloaded library anymore. You can close it and save our library. I'm going to delete this downloaded file, and we can finish our symbol. So update the designator and comment and description, and of course also we need the LCSC parameter. So just paste it here and also copy the LCSC part number from their website. Okay, now go into our schematic, select our library and drag and drop the regulator into our schematic. Okay, perfect. Save our schematic. We would like to know how this is connected. So I'm going to open datasheet. Oops. Okay. maybe just search for datasheet of this regulator, open it, and let's have a look if they write something about the connection. This is the basic schematic. Now here output need to be connected to minimum 10 microfarad capacitor, and what else is about the schematic here? Output capacitance. Minimum output capacitor 10 microfarad with ESR 3 ohm or less. Okay, so this is how we need to connect it. Minimum 10 microfarad capacitor. I'm going to have a look. What is ESR of this capacitor? I'm going to open datasheet. This is the one what we already have in our schematic, so maybe it's a good one. And I'm searching for ESR information. Here, this ESR, the blue line is ESR, so 3 ohms or less. And yeah, it looks like it is less than 3 ohms, so this should be fine. Okay, we can place this capacitor on the output of our regulator, and we can place there too, you know, it's a little bit better. We will have 20 microfarad and also ESR will be lower. Now, what about the input? I'm going to have a look what they say in datasheet about this input. They use 10 microfarad capacitor, but if you search for USB 2 specification, there are some restrictions on the capacitance which we can connect to USB, and I'm going to find it in this document so you can see what I'm talking about. Basically, it says here, USB specification limits maximum load to 10 microfarad. So maybe this 10 microfarad capacitor is too big. Maybe we would like to use something smaller. So let's have a look what is the smallest one, what we can connect to the input pin of the regulator. And here it says a bypass capacitor in the range 1 microfarad up to 10 microfarad is enough. Right now we don't have any smaller capacitor which we could connect there. So let's continue drawing our schematic and then we will put it there later. Next, we are going to create this component. It is used to convert USB to serial port, but I don't really like this one because I used it in past. There were some problems. Maybe I would like to use a little bit different component, FTDI component. They are very popular, very well known for this USB to UART function. So we are going to find a chip from this company, this USB to UART chip. Let's have a look what they have. Maybe this one. And okay, I like this. I'm going to double check if they have it in LCSC because it would be useful if they solder down this one. Okay, they have it. So we can create the schematic symbol. We are going to create again very complicated symbol, or do we? Maybe we can import it. Let's see. Oh yeah, they have symbol and footprint in Altium, so we can download the libraries. We don't have to draw them manually. And okay. Save. Let's have a look inside of the file what we have downloaded. Unpacked schematic lib and PCB lib. Okay, delete this one, we don't need it. Name the files properly, so we know what is inside of these libraries. It is the USB to UART bridge. And open the schematic symbol. Simply just drag and drop it into your Altium. And we can use this. So I'm going to copy it and I'm going to place it inside of our library. Okay. Close this one. Save it. And let's have a look. What is this? They set these pins as input, output. They set this electrical type, and sometimes it may be useful, but I don't want this. So I'm going to set all of them to passive. And what we can do, we can actually just add the arrows. We don't have to set the electrical types because the arrows can be useful to see which one is input, which one is output. So I'm going to find this pinout of the chip. We can see the type, output, input, and all these three are output. So I'm going to select them, press Shift, hold it down, select multiple pins, and do not select electrical type, but set this just this like drawing. It's just a graphical element on the pin, and do something similar for the input pins. All these other, they are input pins. And I don't use electrical types because then there are problems when you will be compiling and doing ERC checks. That's why I don't use the electrical type. Don't forget to set designator and comment, copy, description, and the LCSC part number. And it's almost done. This was really quick again. You know, creating libraries, sometimes it may look like it takes a lot of time. It does take some time, but it's not as much time as some people think. So save the schematic symbol library and place this new component into our schematic. Now we are going to have some fun because we need to connect this correctly. How we are going to do it, do you know? Everything is in datasheet. So I'm going to save this. And we are going to have a look what is inside of the datasheet, how they recommend to connect this. There will be some recommended schematics down here. Okay, USB bus powered configuration, self-powered configuration, and USB bus powered with power switch configuration. This is the configuration which we will use mostly. And you can see these USB is connected to the capacitors, but we are not going to put their capacitors because we have these protection diodes. But we still need to place these resistors here. So I'm going to copy this 27 ohm resistor. We already have them, so we don't need to create new symbol. And just paste it here and also here. Okay, connect the chip and connect everything to our connector. Double check if you are connecting the right polarity, okay? Negative and positive. I'm going to place the net names also here because this is very important net, so we would like to use a proper name on this net. Okay, FTDI, USB, and make it a little bit nicer. Okay, save. Now, VCC. There are some capacitors on VCC. 100 nanofarad and 4.7. So we are going to create 4.7 microfarad. And this is good because then we can use this one also for the regulator. It's less than 10 microfarads. So I'm going to find one. Double check LCSC. They have it. Okay, cool. We are going to create a symbol in our library. It's going to be very quick because we already have capacitor symbol in our library. Just import the parameters, copy the symbol, okay, save it and update all the information. So designator, comment, what is the voltage? I forgot. 16 volts, okay, 16 volts. And the last thing is the parameter. Almost finished. Okay, save the symbol and use it in our schematic. Okay, press spacebar to rotate. We also need 100 nanofarad capacitor. Okay, and how is it connected? So these two are connected to VCC. I'm going to draw the VCC connection, connect the capacitors, place ground symbol, okay, and we would like to connect it to this plus 5V. I'm going to place it here. And it's not going to be so simple because if you have a look here, for the other configuration, it's connected actually to VCC3. So I would like to provide more options. I would like to also provide option to connect this VCC to 3.3 volts. So put it down here. And do you know how we are going to switch between these? We will put there 0 ohm resistor. That's something what we need to create. So save schematic, go to DigiKey, and let's create 0 ohm resistor. It's also called jumper. Use our standard manufacturer. We can use this one. Okay. Double check if it's available in LCSC. Perfect. We are going to create it. If you are creating everything together with me, that's really great. You are doing really good job. This is exactly what you will be doing when you are designing boards. Of course, once you have many components in your library, then it's much faster because then you can just reuse the existing components. We are creating so many components only because, you know, we started with no library. In the next project, you don't have to create 0 ohm resistor because you can use this one, what we are creating right now. Okay, and now the LCSC part number. Okay, 0 ohm resistor is done. We can use it in our schematic. I'm going to place it here and also here. Of course, we can connect both of them at once. So in PCB layout, we will use special technique for placement. You will see. I'm going to move this capacitor a little bit because I would like to connect it like this. I don't like to create the cross because then it's not clear if components should be connected or if they are just crossing the line. And I'm going to unfit one of these. So by default, we don't want to fit the one which is connected to 3.3 volts. So I'm going to move it here. As a reminder, we don't want to fit this resistor because then it would be quite problem. We would short VCC plus 5 with 3.3 volts. Okay, it's correctly connected. I'm going to name this net because it is very important net. It is power net, so when we will be doing layout, we would like to know we are doing layout of this power net. And it can be 3.3 and 5 volts, so I didn't put the voltage there. Save our schematic. We are going to connect this 3V3 output and VCC IO and this capacitor, 100 nanofarad capacitor. So first connect these two pins together. And instead of one capacitor, I will place there two capacitors because we would like to have one capacitor close to each of the pins. So one close to this 3V3 and one close to the VCC IO. So this is the second 100 nanofarad capacitor. Connect it. Okay. Save. Next, reset. Maybe I don't want to connect the reset directly to power. Sometimes it's very useful to have option to disconnect it. So I'm going to use 0 ohm resistor like this and connect it. So in case I need to manually reset or I need to probe the reset, disconnect the reset, I just desolder the 0 ohm resistor and I can do with the reset anything what I need. For this circuit, you can see they don't place 0 ohm resistor on this pin, but from my experience, it may be useful. But by default, we don't want to connect this 100 nanofarad capacitor, and we would like to fit the 0 ohm resistor. I'm going to name this net. Again, this is power net, very important power net, so I'm going to call it plus 3v3 underscore FTDI. Okay, and it's starting to look really good. What else is missing? This one is connected. To support this one, we already add support for this, and this, what does it say? 3v3 regulator output. VCC must be greater than 3v3, otherwise 3v out is input which must be driven with 3.3 volt. So we need to add support also to connect this plus 3v3 FTDI to connect it to 3.3 volt. In case we would like to try also the different operation mode for this chip. It's only for testing. Okay, so this is okay. Now this, we would like to support also this. For this self-powered configuration, we need to add 2 resistors connected to VBus sense pin. First, we need to create 4K7 resistor. Let's do it. Now you can do it with your eyes closed. I'm pretty sure. Okay, I'm going to use this one. And double check it. I'm sure they have it because this is quite standard resistor. So let's create it in our library very quickly. Search. Now import. Copy the symbol. Paste it. Okay. And update the information about this resistor. Copy description. And set the parameter. Copy. Paste. Save. Okay. VBus sense. So where is the VBus sense pin? Oh, okay. It looks like it's available on CBus pins. CBus 0, 1, 2, and 3. And you can configure it. So basically we can connect it to any of these pins. And then you just configure it. You just configure the function of the pin, which we will use. So I'm going to create the voltage divider here, 4K7, 10K, and I'm going to connect it to this CBus 3 pin. Again, this is something what by default we are not going to use it, so it's not really like super important, but we would like to have it ready. Connect this 10K to ground and 4K7 to plus 5 volts. We would like to have it ready in case we would like to experiment with different options, how to power up this board what we are designing, because maybe you don't want to power it up from USB. Maybe you would like to power up this board from header. So then this can be super useful, all these kind of configurations. Okay, this is very important net, so name this net and save schematic. I'm going to add a node just you know, so we don't forget what kind of support we created in this schematic. So if in self-powered configuration, then set CBus 3 as VBus sense. Okay, that's the alternate function of the CBus 3 pin. And you can do it through this software utility, ftproc. And I will add one more resistor here, just for fun. Now, you know, in case you would like to use or you would like to test different feature, you can probe this 10K resistor and you can, you know, use this because the chip itself, it has like very small pins, and if you would like to use some of these alternate features for something special, it would be very hard. So that's why we also use this 10K resistor. All this is connected. This needs to be connected to ground. This is going to be very simple. Okay, and these pins, we don't need to connect them, so I will mark them as not connected. And let's have a look on this, on the UART interface. How do we need to connect this? So we only need the 4 pins. We need the RX, TX, DTR, and RTS. All the other pins are not connected. And we need to place net labels here, so then we can easily connect the pins with other circuits which we are going to create. Okay. Don't make mistake. Very important, super important. Most common mistake, one of the most common mistakes is swapping or not swapping RX, TX when connecting serial lines. So be very careful, mark them correctly. Now, let's have a look how they are connected. So TX is connected to RX pin of the module, see? And is also connected to the header. And the TX or the RX pin of this FTDI needs to be connected to TX pin, which is on the header, and also on the ESP32. So what I'm going to do, I'm going to add these resistors here. But first I will make this a little bit longer, because this will go also to the headers. So I will make it longer. And here I will also then add the resistors. I'm going to use 0 ohm resistor. And when we will be connecting this ESP32 module to the USB to UART bridge, we need to swap RX and TX. Very, very important, okay? So notice how this is going to be connected. I'm going to copy these net names. TX is going to be connected to RX, so here, okay, and RX of this FTDI bridge is going to be connected to TX of ESP32. Be sure it is connected correctly. Super important, super important. As I said, one of the most common mistakes connecting this wrong way. Save schematic. Now this DTR is connected here, and this RTS is connected here. So we need to create this circuit. Okay, we have the resistors, but we still need the transistors. So I'm going to copy this name, and I'm going to search for the transistor in DigiKey. Do they have it? Here are some transistors. Okay, looks like we can use this one. So double check LCSC. They have this. Okay, so we can create the symbol. Paste, search, import. We can download the libraries. Because you can see symbol and footprint already exists. It will save us some time. Go inside of the downloaded file, unpack the schematic and PCB libraries, delete the downloaded file, rename the libraries. So we know this is the transistor. We will later need this when we will be creating footprints. Now open the schematic symbol library. We can copy this symbol and simply place it into our library. Okay, close the downloaded library, and we need to also adjust the parameters. So designator is going to be Q question mark, comment is the part number, description is from DigiKey, and LCSC part number is from their website. Copy, paste, save. Let's have a look how this transistor is connected. So we need to create this circuit, which is here. We are not going to fit 0 ohm resistors, but we still need to place the transistors into our schematic. So I'm going to do it. Find them in our library and simply just drag and drop first transistor. And we need one more. Okay. Now let's go back, and we also need to be careful about how these transistors are rotated. So use flip X and Y command, flip the transistor and be sure the arrows are correctly connected. And now 10K resistors, remember, connected this way. So I'm going to find 10K resistor, let's say this one, copy. And I'm going to place 2 of them here. Be very careful about the arrows, okay? In the transistor, they have to be facing the same way as what you can see in my schematic. And connect the rest of the circuit. This circuit is used to help when we will be using the USB to UART bridge to program our board. That's why we need this small circuit. Okay, we need to connect it to existing signals. So let's have a look. DTR RTS. I'm going to find these signals on the bridge. I'm going to copy DTR. Don't make mistake. Place it correctly. Now RTS, place it here, and the other end GPIO 0 chip PU, GPU, copy, paste, and we split GPIO 0. So I'm going to use this one, button GPIO 0, place it here. Okay, save our schematic. I'm going to name this subcircuit serial signals handling, and let's name also the other parts of our schematic so everyone knows without actually reading datasheet or looking very deeply into schematic. Everyone will know based on this description what these parts of our schematic are doing. This one I'm going to call 5-volt power selection. Save. And now we can finish this regulator. Okay. Open datasheet. And on the input, do you remember what we need to place? 1 microfarad to 10 microfarad capacitor here on the input. We already have this 10 microfarad, 10 volts, but we created this one 4 microfarad, 4.7 microfarad, 16 volts. This is better capacitor, so I'm going to connect it here, and we are going to use it in this circuit. This is super simple circuit. It has to be connected like this. Okay, just input and output capacitors. We don't have the resistor dividers because that's a little bit different variant of this chip. This one, what we are using, is fixed. It has fixed voltage output. Don't forget to connect the ground pins. Also here. And place the power ports. So on the input is going to be 5 volts. And connect. Output is going to be 3.3 volts. So I'm going to name it like this, plus 3v3 underscore reg. It's like it's output from regulator. Okay. Don't forget to name this subcircuit. I'm just going to call it 5 volt to 3v3. Okay. Save. And what now? Now we can connect these headers. This is going to be fun. And there is only one ground, and I would like to have a little bit more complicated this. I'm going to make it a little bit more complicated. I would like to have more pins and more grounds. So I'm going to use a little bit longer header. I'm going to find it. I always make things a little bit more complicated. We didn't use same USB to UART. We are going to use longer header, but it's because I would like to improve it a little bit. You will see how we will connect the extra pins. We will connect there the ground and also power because it's very useful. Okay, they have this in LCSC, so we can use it. I'm going to copy DigiKey part number. Import the parameters from DigiKey. And And to draw the symbol is super simple. These are just pins. So place pin, press tab. We are going to start from 1. Okay. And we would like to place 2 extra pins. So instead of 22, we are going to place here 24 pins. 22 is in the original header. Okay. Big yellow rectangle. Don't forget to move it back so we can see the pin names. Okay. Update designator. Comment is going to be part number. Description from DigiKey. And LCSC part number parameter. Copy it from LCSC website. Save. Now we can use it in our schematic. Drag and drop it. We need 2 of them. To flip, use X or Y. Okay, I would like to see what nets are connected in the original schematic to the pins. Pin 1 and pin 24 are the extra pins, so I'm going to start with pin number 2. This is going to be the first pin from the original header, and now connect all the other. Same as before, copy and paste multiple lines, it's going to be easier. Pin number 2 on this header is going to be basically pin number 1 on the original header. So I'm going to start from this GPIO 0. It is this one. We already use it in our schematic, so I will just copy and paste it here as pin number 3. And now GPIO 1 to 18. Place net label, tab. And we are going to do it this way because then it will automatically increment. So GPIO 1, 2, 3, 4, and do it up to 18. Okay. Now this one is going to be extra ground, and also pin number 23 is connected to ground, and this one is plus 3V3, and we would like to use 100 nanofarad capacitor close to this pin, or I would like to use it. Maybe you don't want to. You can see in the original schematic there is no capacitor, but it's very useful to place these capacitors close to the power pins on headers and connectors. So that's why I do it. It can help with some filtering and maybe improve a little bit the power. And here is the 5-volt power. Again, I'm going to put there first the power port and then 100 nanofarad capacitor. Okay. Perfect. And pin number, first I'm going to connect also this ground. Pin number 24, we will just leave it. In case you need this pin, you can just use it. we will leave it unconnected. Copy these wires from the first header, because it's faster and easier, and we need to place all these net names there. And also be careful about these USB GPIO 19 and 20. So let's start with something. So I'm going to start from GPIO 21, and the USB we will connect a little bit later, the GPIO 19 and 20. Have a look how we need to place the net names or net labels. Be careful, don't make mistake, okay? Follow the original schematic. Do it like this. You can delete this. Now I'm going to connect here the chip PU. Okay. Then this one is RX. And this one is TX. Okay. Few more pins, what we need to connect. This one is ground. And I will connect also pin number 24 to ground. Here I'm going to connect 3.3 volts. So we have, this way we can have the power also on the second header if we need it. And now the USB. And USB signals are very important, so I'm not going to connect them directly. I'm going to use again 0 ohm resistors, same technique as what we use for GPIO 0. So I'm going to place them here, and I'm going to split them. And I'm doing this way because USB is sensitive for PCB layout, and by using these 0 ohm resistors we can reroute these USB signals between the header and connectors. Okay, so let's be very careful about NP, and I'm going to connect first to, this is going to be our default option. Double check polarity, and the second two I'm going to connect to the header, and by default these will not be connected. So by default we will not fit these two 0 ohm resistors connected to these two signals. Again, double check the polarity, be sure it is correct. One of the most common mistakes what you can find in schematics if you are not careful, that people swap P and N signal and connect it to our header. 19 is N, so this one needs to go here and this one needs to go here. Okay, I'm going to make this a little bit longer so it looks nicer, and Perfect. Save schematic. There is one more thing what we would like to specify for these USB signals. We would like to mark them as differential pairs. Do it this way. And place them into special differential pair class. We are going to call it diff90. This way mark all the differential pairs. And because we use the _n and _p in our schematic in the differential pair net name, Altium will automatically know which of these signals is negative and which is positive when we mark these signals with this differential pair directive. So these two are not going to be fitted by default. Place there the NF text and save our schematic. I'm going to add a note about this +5 volts just to remind us how we can use it or how we can connect it. So here I'm going to write design node and +5 volt can be possibly used as an input power if configured correctly. Okay, so if you have time, you can experiment with this, especially if you would like to power up your board from the headers. I'm going to name this small subcircuit very simply headers. Okay. Save schematic. And now we need to do something with this output from the regulator. We are going to use a very similar way as what we did for power selection. So we are going to find a jumper which we will use to connect the output from the regulator to the 3.3 volt of our board. And okay, this is something what we could use. And we are going to do it this way because, again, if you would like to maybe use 3.3 volts coming into your board through headers, you can very simply just disconnect the regulator, onboard regulator, by unfitting this jumper. It's going to be very simple to create it. It's instead of 3 pins, we are going to use 2-pin header. So I will copy this and simply just delete one of the pins, pin number 3 to be specific. Okay. Update designator. Copy part number to comment. Okay. Almost finished. Copy, paste, save. We are going to place it inside of our schematic. And by default, this is going to be fitted, okay? This link on this jumper is going to be fitted. So the output of the regulator will be the main source of the 3.3 volts to power up all the chips on the board. So I'm going to copy the output from the regulator on one side to pin 1, and board 3.3 volt is going to be on the other side. And by using the link, we will short these two together. Okay, again, you can use it for experimenting, okay? Three v 3 power selection. Okay, and here I'm going to add also 3 v 3. Perfect. Save our schematic. And what else is missing? LED. This is the last circuit which is missing, power LED. So I'm going to find green LED. Sometimes, I don't know why, sometimes they use red LED on power, and I think green LED is much better to say everything is okay, board is powered up, everything is green, let's go. So I'm going to use this one and double check if they have it in LCSC. It's not really like super critical what kind of LED we use. Let's have a look if we need to create symbol. Yeah, we will need to create symbol, but you can do it. You know exactly how to do it. So place pin number 1, make it a little bit shorter, press spacebar to rotate if you need, like this, and place the pins. Hide the name and designator. Be sure pins are facing out of the symbol. The white side of the pin is facing out of the symbol. And I'm going to change this so I can see the grid. Press G, make the grid smaller. And let's draw the LED symbol. Okay. Don't worry, it's going to be super simple, very quick. Do it exactly the same way as I do it. You can see the position of my cursor. Okay. And the arrows. Press spacebar to change the way how the line is drawn. We need one more. Okay. Okay. So this is very simple symbol of a LED. Don't forget to change the grid back to 100 mils. Save it and update the properties of this symbol. Okay, the parameter, and LEDs are always super useful. So in our board we will not only use power LED, but I would suggest to use also user LED. So once we place this power LED into our schematic, simply just drag and drop it. We will then also create user LED. But there is one more thing what we need to connect to this LED circuit. Do you know? There is always a resistor. So in our case, I'm going to use 1K resistor. I'm going to search for it. And it's 1K because from my experience, this is some 1K will generate the kind of light which is okay for this kind of LED. Some of the LEDs, they are super bright. If you use lower resistor, maybe like 500 ohm or 300 ohms, they can be very, very bright. It can be disturbing. So 1K is just right for me. If you like, you can use smaller resistor. So we need to create this one because we don't have it in our schematic symbol library. And it's going to be very quick because we can copy and paste the symbol. We just need to import the parameters. Okay. Almost finished. Okay. Pin number 1. Few more adjustments. And we can almost use it. One more thing. Okay. And copy, paste, save it, go to our schematic and connect this to our LED. We would like to connect one side to ground and the other one we will connect to 3.3 volts. You can connect it also to 5 volts, but I like to connect it to 3.3 volts because then you know your regulator is working correctly. Save schematic. And I'm going to put here name. So everyone knows this is power LED. Okay. Don't forget to save. And as I said, we are going to copy this and we will create user LED. But we would like to use maybe different color. So I'm going to search for red LED, or you can use orange or blue or, you know, any color you like for your user LED. But I will use red because maybe you would like to use it if there is an error or something, you can flash it. And we need to create it because we don't have it in our library, but it's going to be fast because we already have the symbol. So import, copy the symbol, and I think this is the last symbol what we are creating for our schematic. Well done. I think this is, our schematic is almost finished. Copy, paste it here. Of course, there are few more things what we need to do in our schematic, but this is the last component. Okay. So I'm going to copy this. Now I'm going to use the red LED. Be sure you connect the LED in the right direction, okay? And I'm going to connect this to a GPIO pin. And I'm going to use this GPIO too. You can use any pin you like, or you can double check what other pins are used by default on the other development kits and use the same one. It's really up to you. Okay, user LED. Perfect. Save. Next, we are going to update these reference designators. Right now, they all have question mark. Some of these I would like to assign manually. This one I would like to have J1. This one J2. Do it also in your schematic, okay? Change this to J3. This one is going to be J4. Then also this ESP32 module, I would like to call it U1. And all the other we will assign automatically, okay? So go Tools, Annotation, Annotate Schematics. Okay, watch right now everything is question mark, but when I scroll down, these are already assigned. So when I click on Update, you can see Altium is suggesting 61 changes, and watch. Here are all the suggestions, and these are still assigned by us, and these are automatically assigned. We still need to accept changes, so this is what is going to happen, validate changes, be sure everything is green, and watch what's going to happen, okay? Execute changes, and everything was executed correctly. All the reference designators, rest of them, all the reference designators with question mark, now they have numbers. Okay, double check your schematic, double check all the connections, the reference designators, and I notice we need to assign this differential pair property also to these USB signals, okay, and also we need to assign these also here. Okay, keep checking your schematic. Okay, be sure the reference designators in your schematic are exactly same as the reference designators in my schematic, then it may make the layout easier. Here is missing this directive, it's not connected. Okay, compare reference designators in your schematic, double check all the connections and everything, very important. Okay, so this is whole schematic. Now we can save it, right click, validate PCB project, and let's have a look if there are any errors. Oh, many errors, all of them are about missing footprint. So what do you think, what we are going to do next? We are going to create footprints. Go inside of our PCB footprint library, and this is the first footprint what we are going to create, the one which we downloaded. So open the downloaded library, just drag and drop it into Altium. Here it is. And inside of this library, there are 3 footprints, A, B, C, and this one. So A, if we have a look, what are the differences? A has the biggest path. So I selected the path, and here you can see the size, 6524. If I select the second footprint, B version, then the path is a little bit smaller. And this is again smaller, and this is I'm not sure, so we are going to use this B one, the middle one. So copy it, go inside of our footprint library, and right click, paste one component. We can close the downloaded library, go inside of our library, and we can also delete this default footprint which was created when we created the library. Okay, so this is our very first footprint, and save it. And there are many layers. Okay, here you can see all the layers. You can also change the settings and visibility. This is the top layer, the red one is top layer. bottom layer mechanical, top assembly, top 3D body. So there is 3D view. You can do it this way or press number 3 on your keyboard. You can go into 3D view. You can see the 3D model. Press Shift, hold it down, and press right button, hold it down. You can move the canvas. Go back to 2D layout mode, and let's have a look what other layers are here. We don't really need many of these. We need this one. This is the white color on PCB. Bottom overlay, top base. We also need this one. This is useful for soldering components. Top solder, that's for the solder mask. And later you will see which of these layers we will really need. But we can keep all these layers here. After the import, it's fine. We will just not use them in the final production documents. So, okay. Go inside of our schematic symbol library, find the transistor, and now we need to assign the footprint into our symbol. So browse in our PCB library. Here is the footprint, what we have just created, okay. And watch, okay, now this transistor has footprint. But in schematic, transistor still doesn't have the footprint because we have not updated our symbol yet. So what do we need to do? Do you remember? We need to save schematic symbol library, then right click and update schematic sheets. Okay, this will update our symbols if they are already used in the schematic. Now when I select the transistor, you can see they have footprints assigned. This one doesn't have because we haven't created the footprint for resistor yet. Okay, save the schematic. Now next footprint, this one, just drag and drop into Altium. Again, there are 4 footprints in this downloaded library. We are going to use the B one, copy it inside of our footprint library. Okay, very similar, many layers. You can double check what is on these layers. We can also have a look on 3D view. Okay, press Shift, hold it down, press right button, hold it down. Go back to 2D view. And we can save the library. Don't forget to save it, otherwise you will not see the footprint when we will need it. Close the downloaded library, go into schematic symbol library, and here add the footprint. So if you wouldn't save the PCB library, you wouldn't see the footprint in this list. You have to save it always. Now update schematic. Okay, we can double check if we can see the footprint there. So this is the component and here is the footprint. Perfect. Okay, this was very quick. Next one. Drag and drop it. Okay, inside we have 3 again. We can use this one. So copy it. Paste it inside of our footprint library. Okay. Double check 3D view. Looks very nice. Perfect. Go back to 2D view. Save our PCB library. Close the downloaded library. Remember the component name. And inside of our schematic symbol library, find the component. Add the footprint. Find it in the list. Okay, okay. And save. Don't forget, update schematic. and double check our regulator. Okay, it has footprint. The next one what we downloaded is this one. It's footprint for the USB-C connector. Here is only one footprint, so copy this one and paste it inside of our PCB library. Oh, very nice 3D model, I love it. Okay, save it. We can close the downloaded library. Remember the component number. Find it in our schematic symbol library. It's the first one. In my case, it is the first one. And assign the footprint to our USB-C symbol. Update schematic, don't forget. Okay, and double check. Perfect. Okay. And the last one from this list. So these are the super easy footprints. We don't need to do anything. We just copy and paste them. This can save a lot of time. Oh, this 3D model doesn't look nice. Okay, maybe we should find something different. I'm going to save it. Let's have a look. What is the part number? I'm going to copy it. And let's have a look if we can find nicer 3D model somewhere. Hmm. 3D Content Central is really good website for 3D models. Oh wow, this is much nicer. So I'm going to download step file. Okay, download the file. Here is the file what we have downloaded, and in our project directory I'm going to create new directory 3D, and I'm going to copy there the step file what we have downloaded. Now go back to Altium, go back into our PCB library. I'm going to delete this old model, and I'm going to add the new one, the one what we have downloaded. So it is in this 3D directory, select it, and we need to place it. Just left click, escape, and double check 3D view. Okay, that's not, we need to rotate this. So I'm going to change this to 180. And cool, perfect. Much nicer than, you know, all black. I love it. Okay. 2D view mode. And we can save it. We can close the downloaded library, and in our schematic symbol library we can assign this footprint to our switch or button. Okay, okay. Save it and update schematic. Okay. Looks good. Save it. Now Next, maybe these resistors. Well, there are many resistors. So what can we do about them? I'm going to search for one of the resistors in DigiKey, and sometimes they have 3D models. So, oh yeah, they have, see, click here. Ultra Librarian or Snap Magic. There are two places. So I'm going to download this one. I like it more. Okay. This is the file that we have downloaded. Unpack this integrating library. So this time it's a little bit different file. This file includes the schematic and PCB library together. So just drag and drop it, and we have to select extract. Okay. Now you can see we can open the PCB library, and there is only one footprint, so I'm going to copy it and paste it inside of our PCB library. We can close the integrated library, which we downloaded from Snap Magic. Save our PCB library, and let's have a look what we downloaded. 3D model looks good, but I can see there is the white outline missing around the component. If we have a look on different component, this is what I'm talking about, this yellow layer and maybe this cross or other layers. To draw the outline, click on this top overlay, make it active, then place line, and we are going to draw on this layer. We would like to use 6 mm line width. Press G or G on your keyboard, change the grid, and draw it like this. Okay, so right now we are drawing on top overlay because it is active layer, and this is going to be the white line around our resistor. Save it. Okay. Press Shift S. You can activate single layer mode. Shift S. And press Shift S again, or press Shift S again. You can change different kind of modes. You can see. You can cycle between different kind of modes. Now I'm back in the standard view. So press Shift S again, and you can see the white outline is around our component. Okay, be sure library is saved. Go into our schematic symbol library, and we are going to assign this footprint to all the resistors. Be sure you are doing this correctly. And I would like to say, right now what we are doing, we are creating these footprints as quickly as possible. If you will be doing this professionally, then maybe you would like to be consistent with the layers what you would like to use in each footprint. Right now we just use the layers which were created when we downloaded these footprints. Okay, so each footprint has different layers. In your professional library, you would like to use same layers for every component. But in our case, this is fine. If you would like to learn more, watch our courses at FEDVEL.com. They will explain how to create professional libraries. Okay, almost finished with the resistors. Almost all the resistors now, they have the resistor footprint. Okay, now we need to update the schematic. You need to do it one by one. When you are in this schematic symbol library, you need to do it one by one, because I think I tried to select multiple components and it didn't want to update all of them at once. So do it for each resistor type, and it looks everything is okay. Save our schematic. Now next, capacitor. There are many capacitors, so we are going to do something similar. We are going to find a capacitor in DigiKey, and we are going to have a look if they have 3D model. Okay. Oh, download limited. So let's go on this SnapMagic website. You need to register, but it's completely free. So just register and then you can download the footprints and symbols and models from this SnapMagic website. Okay. Here it is. There is the integrated library. So drag and drop it into our project. And also there is the 3D model. So let's open it in Altium. I'm going to open the integrated library or extract the integrated library. And let's have a look inside of PCB file. But I think the inside of the PCB library, I think it will have 3D model included there. Let's see. I will copy it inside of our PCB library. And we don't need this anymore, so I can close it. Let's have a look if there is 3D model. Oh, there is not. So we need to place it there. Click on place 3D body and select the one which we downloaded. Left click, place it into our footprint, and we need to move and rotate this 3D body. Tools, 3D body placement, align face with board. Select the path, and Altium will automatically place and rotate the model the way it will lie on the PCB. We still need to move it a little bit. Do it exactly the same way as I do it here, okay? Follow everything what I do. Perfect. This looks perfect. Okay. Now we can save it. And maybe what I would like to do, I would like to draw the outline around the whole capacitor footprint. So again, on top of overlay layer, we are going to draw this yellow line, or basically it's going to be white line on our PCB. Watch the position of my cursor, okay, if you are not sure where exactly I'm drawing the line. Okay. I like it. Let's double check. Perfect. Be sure it is saved. And now we can assign this capacitor footprint to all our capacitors. All 402 capacitors. Okay. Find it here. Exactly same as for the resistors. We have to do it manually for every single one. There is also a place where you can do all these library updates all at once, but this is much faster and easier and more simple to explain in this very simple tutorial. These are only few components. Double check if footprint was assigned correctly. Okay, looks like the capacitors, they have footprints. We can save our project. What next? We can go in the order. So the first one we already have, and we don't have this one. So we need to create footprint for this header. Go to Digi key. I will close this. Okay, and search for our header. Let's have a look inside of datasheet. This is not what we need. Maybe this one. And we are going to create footprint for this component. We are going to create it from scratch by ourselves. So we need the dimensions and also the hole size. Okay. Go to Altium, and inside of our PCB library, Tools, Footprint Wizard. Click on Next. This is the one what will be good to start with. Mills, Next. We need to put here some dimensions. So the hole size is going to be 40 mils. And this other size is, from my experience, I put here 64. This is big enough for good soldering, and there is still space between the pins. Let's have a look what is the pitch. 100 mils. And this is not really important because we will delete the second row. Now here we would like to have 48 because on one side we would like to have 24. We will delete the other one and we need 24 pins. And I'm going to call this header like this. So when you see this in the list of all the footprints, you can immediately know what this footprint is about. Okay, save. Now, as I said, we can delete half of this component because we only need the 24 pins. And we are going to make some adjustments. So change the grid. Be sure you are drawing on top overlay layer and draw the outline around these pins. Okay. Press Shift S to select everything on top overlay layer, and I made the line a little bit wider. Okay. Save it. And we still need the 3D model. So click here to download 3D model. Here is the file. Go inside. Copy 3D model into our project. Now we need to place it. So select it, press left click to place it, and I'm going to adjust the rotation, and we also need to move it. It's not exactly lying on the board, so use this align face feature, select the model and then select the surface which you would like to have on the top of the PCB. And we would like to place it into middle, so I'm going to move this 0, 0 position to center of our footprint. Now hold the 3D model, hold it in the middle, not here, okay, not in the corner, hold it in the middle. You can see cursor snapped exactly into middle and place it into the center of our footprint. Don't forget to place the 0, 0 position back to pin 1 and double check if everything is okay. Looks good. Okay. We can save our footprint. I noticed I placed this 3D model on mechanical 1 layer, so I'm going to change it because on these other components you can see I'm using top 3D body. So select 3D model and place it on top 3D body. Okay. We would like to mark pin 1 location. So we would like to maybe place text like number 1 there. But first I'm going to double check JLC PCB capabilities. Because we are going to manufacture our board in JLC PCB and we would like to know what is the smallest text what we can place on our PCB. 6 mil and 40 mils. That's what we are going to use. So on top overlay layer we would like to place string. And now here I'm going to put 1 and what is the text height? 40 mil and the width is 6. Okay, so this is the smallest text what we can use and place it close to pin number 1 on our header. It's very useful always to mark pin number 1, especially on headers and also chips. Okay, save it. Now go into our schematic symbol library and we are going to assign the footprint to our symbol. And of course we also need to update our schematic. Double check if everything is okay. Okay, I can see the footprint, also 3D model. And now let's do also the other connectors, when now you know exactly how to do it. And first one, we are going to create this 3-pin because it's very easy to create 2-pin from 3-pin. You just delete 1 pin. So first, let's create footprint for this 3-pin header. And again, maybe we would like to create it manually. So I'm going to search for datasheet because it's not very difficult to create it. And also I would like you to learn how to create footprints by yourself. So you can practice. Single row, okay, this is what we need. Here is all the information, what we need to create the footprint. Go back to our PCB library, and we are going to do it same way. So tools, footprint wizard, next, use this one, mils. Now the whole size, so let's have a look. Actually these are squares, so we need to double check what is the whole size what we need to fit this square pin. So I'm going to use this simple calculator, 16 mils. So we need like maybe 28. So we are sure we can fit the header there. And put there 40. Again, this is from my experience. It's big enough to solder it and also keep space between pins. Double check the pitch, but this is the small one, 1.27, so 50 mils. This is not important. We would like to have 3 pins on one side, so 6 in total. And again, use the kind of name which is very clear. So from the list of footprints, you will immediately know what is this footprint about. Next, finish. Okay, we need to delete half of the footprint. Now we are going to draw the outline, but first I would like to change the grid. And I'm going to do it based on the dimensions. So here I'm going to put 42.5, and here I'm going to put 10 mils. Okay, be sure we are on top overlay, and we are going to place line. And because we have this very special grid, it's going to be super easy to draw the outline around the header. So right now you just learn how you can create your own custom grids. Sometimes super useful. What else we need? We need 3D model. So let's download this. Okay. Here is the file. Copy 3D model into our project. And in Altium, place it. Just left click, escape. Let's have a look. Okay. Tools, 3D body placement, align face with board. First click on the 3D model, then on the surface, which should be touching the top of our PCB, and now we need to place it into middle. So again, same as before, be sure you are holding the 3D model in the middle, okay, and place it on the top of the pin which is in the middle. Everything looks okay. We can save our footprint, and we would like to also place pin number 1 there. So I'm just going to copy it and paste it here. Okay, we are finished. Save. Assign this footprint to our symbol. Update schematic. Double check. Okay. And we are going to do something similar for the 2-pin header. It's going to be very quick because we can simply just copy and paste the footprint what we created, and we are going to make a few adjustments. So I'm going to rename it. It's going to be 1x2. Save. Now we are going to delete 3D model and delete the 3rd pin. I'm just double checking where we need to move this. Do it exactly the same way what I'm doing here in the video. Okay. So you don't have to always draw it, you can also write the numbers or change the properties. I'm going to find 3D model, so I just copied the part number and go to Samtech website, find the 3D model. Here it is, download it. Okay. This is the file. This is the 3D model. Go back to Altium. And in our footprint, we would like to place the 3D model. So be sure you are on top 3D body layer and just place it. Same as before, in 3D view, we would like to say what is the surface which is touching PCB. Here it is. And we need to place it into center. So I'm going to move the 0, 0 position to center of our footprint. It's moving in very small grid, or it's not snapping. Snapping looks okay. It's just very small grid, so I'm going to move it like this. Perfect. Double check in 3D view. Everything looks okay. Don't forget to place 0, 0 position back to pin number 1. For this through hole headers, we would like to have it on pin number 1. And assign the footprint to our symbol. Okay. Save. Update. Double check. Perfect. What is next? Something challenging. We have this one, we have this one, we have this one. Here we are going to create footprint for this protection. So find it in DigiKey. There is no 3D model, so open datasheet and find information about footprint. Here, this is recommended soldering path layout. That's what we are going to create. And we are going to do it because I would like you to learn how to create footprint by yourself for any kind of component. And this is kind of standard SMD component. So we already learned how to create footprints for through hole headers. Now let's learn how to do it for SMD component. Next. So this time we are going to use something different. You could use capacitors, but I'm going to use these resistors. Very often I start with these resistors in millimeters. Now SMT, and here put the dimensions of the paths. Okay, so each wizard looks a little bit different. Here I'm going to put 0.65. Each wizard looks a little bit different because you know, these components are a little bit different, so the wizard will help you to create specific component. That's why we selected resistor this time. Okay, it's not perfect. We need to make some adjustments. So I'm going to work with top overlay and delete everything. Press Shift S, okay, don't forget Shift S, go to single layer mode, and we are going to draw it again. So be sure we are on top of the line, 6 mil, and watch the grid and also position of my cursor, and draw the outline maybe like this. Okay. Okay. Perfect. Now, what do we need to do now? We would like to find 3D model. So on the manufacturer website, I'm going to double check. Oh, they have 3D models. Okay. So I would like to download the step file. Here is the file. And this is the 3D model. Be sure you are on top 3D body and place the 3D model into our footprint. Left click escape. Let's have a look. Okay, we need to use the super useful feature, tools, 3D body placement, align, face. And also we need to rotate the component a little bit and place it into middle of our footprint. Okay, grid is again very small, so I'm going to change it. Perfect. Double check. Cool. Looks very good. Save. And assign the footprint. So you just learned how to create footprint for SMT components. And it was not very complicated. Some people, they are really worried or they are really afraid of or scared creating their own footprints. You don't have to be, okay? Next one, what we are going to create next? We have all these. Oh, ESP32. Okay. This is going to be challenge. Let's have a look what we can find on internet. So this time I use this Snap Magic. They used to be called Snap EDA. Now they are called Snap Magic, and they have many footprints. So let's have a look if they have ESP32. Oh, they do. So we don't have to create it manually. That's very good. I'm curious how it is going to look when we import this into Altium. This is the file what we downloaded, so I'm going to copy it into our project. And we are going to open this integrated library in Altium. Just drag and drop it there. And let's have a look what they have inside. PCB library. This looks good. This looks really good. So I'm going to copy it. Paste it inside of our library. And we don't need this anymore, so I can close it. But what I'm really curious about is 3D model. Let's have a look. Oh, they have also 3D model. Nice, very nice. Okay, let's have a closer look on the footprint. Especially the pins. See, this is not something what we have in our symbol. In our symbol we use like numbers only. These are all the ground pins, and some of them are the extra ground pins. So we need to change these numbers or update these numbers in our footprint. Okay, so 1, 2, 3. This is good. These are the normal numbers for standard pins. 63, 64, 60, 62, 61. So only the pins around are a little bit different. So I'm going to simply just change this to 66, 67. Always select the pin and just change the designator. And we only need to change or update these few pins, and then our footprint is going to show exactly the pins what we have in our symbol. This is very important because this is how Altium knows where the pin in the symbol is connected in the footprint. These numbers have to be same. Okay, 73, that's the maximum number. And don't forget to save it. Go into our schematic symbol library, assign the footprint. Okay, save the library, go to schematic. Oh, we didn't update the symbol, so go back, right click and update schematic. Okay, double check. Oh, okay, now it's fine. Save our schematic. And what is next? We have this one. This one. This doesn't have any footprint. This is a very special component. So everything what we need to do is change this to mechanical. Okay, type mechanical, very important. And that's it. Just save and update schematic. Okay, double check, type mechanical, perfect. And how many we still need to finish? Oh, only one footprint for the LEDs. So I'm going to copy the LED part number. We are going to have a look if we can download something or if we need to create it. What is inside of datasheet? Here is the recommended solder path footprint. So as before, we are going to create this footprint for the green 0402 LED. Go inside of our library. I would like to see also the datasheet. So I'm going to make everything smaller. And you know how to do it. Tools, footprint wizard. And we could use these diodes, but it's not really important. I'm going to use resistors again. There are no big differences between wizard for capacitors, diodes, and resistors. Don't forget we are creating SMT component and use these numbers from datasheet. So 0.7 and 0.6. 1.55 minus 0.6, 0.95. And I'm going to call it LED 0402 green. Later you will see why I put there G. We need to adjust the outline. So press Shift S. You can work with single layer. I deleted the top overlay. Now, this is pin number 1. Pin number 1 is cathode. Very, very important. we have to create pin number 1 in footprint as cathode. So when drawing this outline, I will leave a little bit more space where pin 1 is located, so we can mark this pin number 1 in this footprint. So everyone will know pin number 1 in this footprint is cathode. This is very, very important, okay? Save. Here are the dimensions and positions in case you need to double check it with your footprint. And I'm going to adjust this snapping to grid off. So we only would like to snap to grid and not the other objects. And draw it like this. Okay. Don't forget to adjust size, make it nice. And double check, okay? Pin number 1 is cathode. It is cathode in the symbol and also in footprint. We would like to download 3D model, so I'm going to use this 3D Content Central again, LED 0402, and here are all the kind of colors. So for this one, we would like to use green 3D model. Download it. Here is the file. Copy 3D model inside of our project. And place it on top 3D body layer on the top of our footprint. Let's have a look how this green LED is going to show up in the 3D view. Nice. This looks nice. I would like to see which one is the cathode, but first I'm going to place it on the top of the PCB, and in data sheet, have a look. This is the marker, okay? Cathode. Cathode is this direction, so here is the marker, and this is good. We just need to move it. So 3D model is oriented the correct way. The cathode is on the left. Okay, perfect. And this is 3D model of our green LED. Cathode is there. Cathode, okay. Cathode on pin number 1. Very important. Save. We are going to assign this footprint. So be sure this is the green LED. Update schematic and double check here. Okay. Now we only need to create the footprint for the red LED. It's going to be exactly same as the one what we created, just a different 3D model. So right click and copy, right click, paste. I'm going to rename this to R red LED. Delete this 3D model and go to 3D Content Central, find the red model, download the step file, and we will use it in our footprint. Okay, here is the file. Copy 3D model into our project. Top 3D body, place the 3D model what we just downloaded. And in 3D view, be sure it is placed on the top of our PCB. And just move it. Okay. The marker is pointing to the pin number 1 to the cathode. Save. And this is the last footprint what we needed to create. So assign the footprint to the LED, and we are done with footprints. Save, update schematic. Oh, cool. This is the red one. Save everything. Now right click, validate, and double check the messages. No errors. Yes, 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 yes. Before we import our schematic into PCB, go to Project, Project Options, Class Generation, and be sure these two checkboxes are unchecked, like this. Okay. Now the most important moment, Design Update. And these are the changes what we are going to do in our PCB. We are going to import or add components. We are going to add nets and a few more things, differential pairs. Validate changes. As you can see, most of them will be green. Some of them are red, but this is okay because the net is not there yet. Execute changes. Now, this is important. Double check if everything is green. Everything needs to be green. And it means everything was imported into our PCB. And this is our PCB. Here are all the components, and the black area is the board what we are going to create. In 3D view, we can double check 3D models of the components. It looks really, really nice. Go to View Configuration, View Options, and I'm going to change the white background for something better. So I'm going to use these blue presettings. Now it looks much better. Okay. Okay. Go to 2D view, and there are some green areas. Green, it means there are some errors, but we will fix this later. Don't worry. And if you would like to make some adjustment in the view, then you can do it here in this panel, in this view configuration. If you don't see it, click on Panels, View Configurations, or you can click here on this color. It will also open View Configuration. And next, what we would like to do, we would like to draw board outline. So we would like to create the shape of our board, and we need dimensions. Don't forget, our board is going to be a little bit longer. I'm going to double check what is 25.4 in mils, 1000 mils, because in our board we will be using mils. You can switch between mils and millimeters in Altium, but because everything is in mils, I will keep working in mils. Okay, don't forget, we would like to use something a little bit bigger. Our board is going to be longer because we have 2 more pins. Remember, 1000 and 2470. Now, go to View, Board Planning Mode, and Properties, grid manager. I'm going to change the grid to a little bit bigger so it's easier to draw the outline. And design, redefine board shape. Watch where my cursor is. I'm going to draw it somewhere here, okay? Do it same way. Put it somewhere here. Just left click and start drawing. And keep the size of the board based on datasheet, plus make it a little bit longer. Okay, so this is going to be our board. Go back to the layout mode, and we would like to move this 0, 0 position. So I'm going to move origin to this bottom left corner of our board. I'm going to move these components a little bit up. And we can save our board. Go to Tools and switch on this Cross Select mode. There needs to be this blue frame around this icon. Then once this mode is used, we can select a component in schematic and it will be automatically selected also in PCB. We are going to place the key components, so USB connectors, and hold USB connector here in this pin. So place it like this and watch the position of my cursor, okay? Watch where I'm placing the connector. Okay. Do it also for the other one. But this time we are going to hold it where this other pin is. Okay, perfect. I'm going to save everything. Next, the two headers. And we would like to see how they are oriented on the board. So I'm going to double check. Here is the ESP32, and you can see here is 3.3 GPIO 0, 1, 2, 3. So, and it's 1.27 millimeter from the edge. So it's this header, GPIO 1, 2, 3. We need to rotate it. Press spacebar to rotate. Watch where I'm going to place it. Okay, like this. Okay, this is the header, what we would like to have here. Maybe we would like to have this header from the bottom. I'm going to place this header on bottom layer, but watch what will happen with pin number 1. It's now on the other end, so we have to rotate the header again and place it again. Okay, ground 3.3 volt GPIO 0, 1, 2, 3. And in 3D view, now you can see the header is on the bottom. Okay, so this is what I would like to have in our 3D view when we finish the board. Because this 3D model of your board, then you can use it in your projects. When you finish your board, you will have 3D model of your board. Be sure you place it exactly into the same location where I have it. Double check the pin position. So reset GPIO 46, 5. Okay. Okay, that's exactly what we have here. Perfect. Now, we would like to work with filter a little bit, select all the components, and we are going to lock them, use this lock. So this means you can accidentally move these components. If you would like to unlock them, you need to double click on the component. Reset our filter. Save everything. And let's place the module, ESP32 module. Do it exactly the same way as what I'm doing. Hold it where this pin is and place it here. Lock position of the module. Okay, save our board. And next we are going to place this reset and boot button. So the first one is going to be reset. Okay. Press spacebar to rotate. I'm going to change the grid. To change the grid, press G on your keyboard, go, and place it here, okay? When you select it, you can see the position here. Place all the components in your board same way, into same position as what I'm doing here, because then it will be easier for you to do layout. Be sure the rotation of the switches is correct, and adjust the position, lock the buttons, okay, perfect. Keep saving so you don't lose your work. I land this the hard way. Press spacebar to rotate, place it here, 710 and 770. Be sure pin 1 location you have exactly the same way as I have it, so rotation is 270. Now the regulator, 780, 290, rotation 0. Okay, I'm going to lock this one and also this one. Next, the jumpers, place it like here, 375, 550, and the second one, this is connecting the regulator and 3v3, 1375, 500. Okay, lock this one and also lock this one. We would like to hide these designators. There are many designators and they can be quite annoying, so select filter only. We would like to work only with components and hide designators. Watch what's going to happen. Just click here. Okay, this is super simple way how you can hide designators. Don't forget reset the filter so you can work with the components, and I'm going to move them a little bit closer to the board so we don't have to always zoom in, zoom out so much. And also these two. Perfect. This is much better. Save. You can see how these pins are connected. The yellow lines are showing you the connections. But I'm going to hide it because right now it's really disturbing. We don't really need to see them. And I also reset the errors, so we have everything nice and red. We don't need to see the errors right now. Save again. And these are all the layers which are on our board. So right now we are working with top layer. This is the bottom one, mechanical one. This is very unusual because what is this? These are like 3D models. Let's go back to our PCB library. Maybe I placed 3D model on wrong layer. Yeah, I by mistake I placed it on mechanical one. It should be on top 3D body. If you make any changes in PCB library, you need to update your PCB with this new footprint. So this is how you do it, okay? If you need to adjust any footprint, you need to then update PCB. Now have a look. See, all the 3D models are correctly on this top 3D body layer. Perfect. So we don't really need to see this mechanical one layer. Top assembly. We don't need this one. We don't need this one. We are not going to use these layers for manufacturing, so I'm just switching them off so we don't see so many tabs in this view. Okay, these are like most important layers. Use Shift S to move between single layer mode and the other modes. Save everything. We are going to create this layer set. So this one is going to be default. And we will create them because it's very easy then save some specific views. So this one is going to be the top view. I only enable the layers, what I would like to see in this top view, and save it. Now the next one is going to be the bottom view, and we will enable bottom layer and bottom overlay. Okay, active layer is the bottom layer, save it. Top and bottom. You can create also all this view by yourself, because very often you would like to have a look only on the top layer or bottom layer of your board. So they are very useful. You can switch between them through this LS button. See, LS top, okay? Or you can switch between them here in this drop down. This is the bottom view. Super useful. I recommend you to create this always. Okay, we can save our board. We are going to place components around this connector. So first select this protection and then press Shift, select the other one and also the third one. We have 3 of them selected. You can see all 3 of them are here, and then we can use these tools, component placement, reposition selected components, and exactly in the order how we selected them, we will be placing them on our board. One of the most useful features in Altium. Be sure you rotate the components correctly. You can see where the pins are connected. So I'm going to use spacebar and rotate it like this. Spacebar and rotate and place it like this. Always when you are placing components, think how they are going to be connected to the other pins. Okay. So I'm going to place this one here. These are the protection components. And let's have a look where they are connected. Oh, this one is connected here. Press Ctrl and left click. You can see where they are connected. Okay, Ctrl and left click. And then Ctrl and left click into empty space. And possibly you can use square brackets to adjust the intensity. This is supposed to be connected to this V bus, but I don't see it here. There is something weird. B for So the name of the pin is a little bit different. See, in our symbol we call them differently, so we need to correct these pin names in our footprint. I'm going to remove this, and also here, and here, and here. What do we need to do now? We need to save our library, and then we have to update our PCB, don't forget. Now we have the correct footprint in our PCB, but it still will not be connected. You see, now there are proper names, but they are still not connected. There is no net name. So we have to go into our schematic, and we have to now update PCB with all the connections, new connections to these new pins, what we just created. Okay, so what's wrong? Oh, also these pins, they have different names. So here they are called 1, 2, 3, 4, and in our schematic symbol they are called S1, S2, S3, S4. So we need to also update these pins. Select it, put here S1, S2, S3. So always read the error messages. They will explain very clearly what the problem is. Many people complain they can't fix errors. But if you read the error messages correctly, you will be able to figure out what the problem is. Okay, now this looks fine. Let's try to update our PCB again. Good, validate, perfect. Oh, everything is green. Execute, everything is green. Okay, okay. Reset error marker so we don't see the green color. And now this looks good. This looks correct. Okay. Next, let's place these two resistors. So press Shift, hold it down, and left click, select also the capacitor. Reposition selected components. Okay, so this is the first resistor. Again, watch where it is connected. It will help you to find the right place for the component. Okay. And there is also a different method how you can see where something is connected. You can press Shift, hold it down, and just hover cursor over a path. But I like to do it different way. So in settings, what I'm going to do, I'm going to enable this highlight even without holding Shift down. So I will uncheck this. Now when I hover over a pin, automatically I can see where it is connected. Super useful. Okay, perfect. Perfect. I'm going to save everything. And because we use this component placement, reposition selected components very often, I would like to place it here, some kind of shortcut. So right click here, customize. Find the command here, reposition selected components, and simply just drag and drop it into this component container. Okay, close. Now when you go here, you can see this is the reposition selected component. So we can very quickly access this command because we use it a lot. Also go inside of these nets, and we are going to assign a color to the ground net because there are many ground pins. So I would like to very clearly see which of the pins are connected to ground. You can use same color, what I'm going to use, 2 to 3. Okay. And we need to enable these colors, so enable it, or you can press F5, try F5 on your keyboard. Yeah, it should look like this. Perfect. Okay, you can save the board like here. Now, in this PCB panel, these settings are also important because they can help you when you are working with board. Play with these settings and learn what they do. If your view looks a little bit different from mine, double check these settings, okay? We are going to place components around this second USB connector. So left click to select this one, press shift holding down left click, use reposition selected components, watch where these components are connected and if you need to rotate them, and also have a look at the position where exactly I'm placing these components, and notice where I'm holding these components when I'm placing them. Okay, sometimes I'm holding them in the middle, sometimes I'm holding these components where a path is. Okay, I'm double checking where the paths are connected. Save. Now rest of the components around the connector. Again, use reposition selected components command and place these. Okay. Okay. Next, we are going to place components around this USB to UART chip. So let's start with these USB resistors. Very important resistors. I'm going to place them here. Okay. Next, these capacitors and these 0 ohm resistors, we need to place them close to the power pin. Watch where it is. Okay. Okay. So these are two capacitors and now the 0 ohm resistors, and I'm going to place them very special way. I will place them on top of each other, so we can only fit one of them for safety reason, and then later we will remove this silkscreen which goes over path. Okay, very useful trick, placing components this way. Later we will fix all the errors. For now, just ignore the errors, the green color. These are the coupling capacitors for VCC IO and 3V3 out. So pin 10. This is pin 10, okay. I'm going to place it here. And here is the second pin, so place the other capacitor here. And this is the 0 ohm resistor. Next, reset, pin number 11. You can see where these components are connected. So this is the capacitor, and this is the 0 ohm resistor. Okay. always place components based on the schematic, because position of some of the components is super important. For example, decoupling capacitors, you really would like to place them close to power pins. This voltage divider, it's also useful to place it close to the pin, because you can only draw very short connection. It can make the layout easier. And also, some dividers are important. Now, the regulator. Important capacitors, we need to place them close to the pins. So the input capacitor we would like to place very close to the input pin. And here are the output capacitors, place them close to the output pin. And I'm placing them this way because then there is also very short connection between the ground of the capacitor and ground of the chip. Decoupling capacitors for ESP32, you know where we need to place them, close to the power pin. Where it is? Here, up here. Okay, press spacebar to rotate and place them. See, pin number 3. Double check, pin number 3. Okay. Next, these two resistors are connected to pin number 4. And there is not really much space, so I'm going to place them maybe here, like a little bit further, but it's still okay. You see where pins are connected, okay? I just hover a cursor and you can see where they are connected. These are special resistors again. We will use the special technique to place them so only one of them can be fitted. We will place them very close to the ESP32. So the connection between these resistors and ESP32 is direct and very short. And place the second pair of the resistors and move them on top of each other. Notice I'm holding the resistor where the pin is located, okay? And again, only one of these resistors can be fitted, so it's very safe. You can't fit both of them at once. I mean both resistors on one signal, positive or negative. Now these 0 ohm resistors, I will find some place, maybe here and here. Okay. Double check where they are connected. Okay. Okay, perfect. What else? This special circuit. So select transistor, resistor, transistor, resistor, and place them close to the bridge because there is space, and they are also connected to the bridge, so it will be good for layout. Think about how you are going to connect them, how you are going to do layout when you are doing placement. You would like to make the layout as simple as possible, ideally on one layer, if it's possible. Okay, connected or placed, not connected yet. And here are some components around these buttons. So let's select these two and place them. Okay, perfect. Only a few components are left. So this one goes to the other button. I can place it here. Components around these headers and the LEDs. So first the LEDs. Here is some free space, so I'm going to place them here. Okay, and the second one, I will place the second one on the opposite side of the board. I will double check what is the position. So I will change it. And I like to place it symmetrically so it looks nice. So change position here. Okay. Here are the LEDs. Okay. And double check the orientation. I will rotate this one. Okay. Okay. And this capacitor goes to pin number 2. It's here. So I'm going to select it and place it. Okay. Now this one, pin number 1, it's here, and it's this capacitor C4. Place it close to the power pin. Or the pin with power. And this is the last one. It goes here. Okay, all the components are placed. Now, let's have a look on our board. Wow! This is so cool. This is so cool. We have not connected the components yet, but it still looks really cool. I really hope you like what you have built, how your board looks now, if you are building this board when watching this tutorial. Before we connect this board, we need to set up some rules. So design rules and clearance. This is the space between objects on our PCB. So let's go to JLC PCB manufacturing capabilities, and we are going to have a look what is the minimum trace width and spacing. For 4 to 6 layer, minimum trace width 3.5 and spacing 3.5 mil. In our case, this is 10 mils. We can keep it. 10 mils is okay. And for the width, preferred 10 mils. Max width is going to be a little bit wider, 100. And minimum we can leave 10 for now. Routing vias. So what is the smallest via, what they can do? Not here. here, minimum via hole, multi-layer, preferred 0.2, 0.2 millimeter, what is it? How many mils? 8 mils. Okay. I'm going to use 12 mils. Maybe you don't want to use like minimum values. It can make your PCB a little bit cheaper. And via diameter, I will use 24 mils. Let's double check what is the size in millimeters. So 12 mils is 0.3. The whole size is going to be 0.3 millimeter, and the via size 0.6. That's the 24 mils. Okay. Solder mask expansion, by default, they have 4 mils. Let's have a look what are the capabilities, what JLC PCB can do. Solder mask 0.038, 1.5 mil. So we can maybe use 2 mils. Okay, so double check all these. These are the basic rules, most basic rules what we need to set. Okay, and save. There are still some errors. Can we do something about this? I'm going to double check what are these errors about. Here in this list, component clearance, we know about this because we placed components on top of each other. So there is collision between two components, R24 and R26. See, these are 24 and 26. This is the same error, same problem, and same here, two components on top of each other. Remember these numbers. We can fix these errors. So go to design, rules, and find component clearance. These are the default values, but we are going to add new rules or new rule, and we are going to make this exception R24, R26 component R24. So this is the first object, and the second object is R26, and here we specify distance between these two resistors is going to be 0. Okay, so we created special rule which will basically ignore that these two components are on the top of each other. Do it also for R23 and R25. We need to change it here. Okay, and duplicate again. There is one more exception what we need to create for R1 and R2. I'm going to set it inside of the rule. Okay. Double check all the rules. You need to have them same way. Now watch what's going to happen. Press OK. Oh, okay, they are gone. So these errors are gone, and there are still these errors. So again, let's double check what these errors are about. Clearance constraint. So the paths are too close to each other, less than 10 mils. Okay. If you would like to measure distance between objects, use reports, measure primitives, and select the objects. 7.8 mil clearance between these two objects, okay, 7.8. Let's double check capabilities of JLC PCB, how close we can place paths. path-to-path clearance 0.27. That's the minimum what they can manufacture, and that's 5 mils. Okay, so we can basically create a special exception in rules in our clearance that two paths, minimum distance between path and path can be 6 mils. It means this should be okay for our board. Watch what's going to happen. Okay, error is gone. To clear this one, press Shift C on your keyboard and save our board. Okay. What next? Next, we can start maybe connecting something. Watch where these pins are connected. Be sure you are on top layer, and to do PCB layout or draw tracks. Okay, press tab, you can change the width of the track. Be sure it's 10 mils, and just left click and maybe change the grid and left click. Now we would like to go from the top of our board to the bottom, so I'm going to place a via, and do you remember the size of our via? 24 and 12 mils. Be sure it's set like this and place it. Okay, so this via will help us to go from the top to the bottom of our board. Okay, save. Now make the bottom layer active, and we are going to draw track. We can also do it from this toolbar and simply just connect the via with the path. And this is our very first connection. Yes, finally we are doing PCB layout. Let's have a look where these other paths are connected. This is a little bit complicated. We can connect this next one. So I'm going to copy existing connection. When you use copy command, you can pick where you will be holding the objects after you paste them. So I picked the position exactly where the path is, and then it makes it easier to paste it directly on the top of the path. And now draw the connection on the bottom layer. Go very close to the pins like this. Okay, perfect. Be sure you are on top layer, and I'm going to make this connection a little bit longer because we don't want to have all the vias in one row. And a little bit later I will explain why we would like to have it this way. And this is interesting. You can change routing modes. Watch down here what routing mode you are using. Walk around obstacles. See? Press Shift R, you can change the mode. This one is stop at first obstacle, auto route, ignore. Okay, all the kind of routing modes. You can find them all here, and I will uncheck this because I only use some of these. And when we are here, also uncheck this, allow via pushing. We don't want to push vias when we will be doing layout. So walk around obstacles, Shift R, push obstacles, Shift R, stop at first, and ignore obstacles, walk around. This is what I'm going to use, okay? Walk around obstacles. Use the same routing mode and go around the already routed tracks and the pins. This way we can route very close to the tracks because we don't have much space. We need to route this way. Okay. Now I'm going to copy this and I'm just going to duplicate them. Do it like this, okay? So we would like to have a lot of space between the vias, because when we will be doing power planes and ground planes, we would like this ground to flow between the vias. If we would place them very close to each other, there would be no space for the ground flowing between vias. Later you will see when we will be doing this. Okay, I'm going to copy this one and paste it here, and also here I need to place this short one. Okay, and down here, and also here. These are same nets, so we can place them like this. And also maybe one here. Okay, this will be connected on the top, so we can save our board and we can continue. We don't need to see these layers, so I disable them or hide them, and I'm going to continue doing layout on the bottom layer. Use the walk around obstacles and route as close as possible to the existing tracks. As I said, we don't really have much space, so we have to do it this way. Okay. This is super simple because the connector pinout is designed the way that it's very simple to connect to the ESP32 module. Okay, connect this one and also this one. How do you feel doing PCB layout? I hope you like it. I love it. Okay. Now, I will make it a little bit nicer. You can just hover cursor over the track and then press left button, hold it down, and you can move the track. Okay. Don't forget to save. Before we continue, we would like to place vias for ground and power pins. Do you know why? Because now when we place the vias, then after we continue drawing the tracks on the bottom layer, we can very nicely go around these vias. But if we would continue drawing the tracks on the bottom layer and then we would find out, oh, we need vias in this area, we would have to redraw a lot of tracks which we already created on the bottom layer. So in every area where you are drawing tracks, always place all the vias so you don't have to keep redrawing the tracks after you place the vias there. Save our board, and many pins are connected to ground. So what we are going to do next, we are going to add 2 more layers into our stackup. Search for JLC PCB stackup. We would like to see what kind of 4-layer stackups are available. Here are 4 layers, and this is the one what I like because the distance between top layer and the second layer is very short. So I'm going to keep this open, and we have to switch Altium to millimeters. So press Q, switch to millimeters, because the stackup is in millimeters. Design, layer stackup manager. Wait a little bit. Okay, so as you can see right now we have 2-layer PCB. Keep this checked, and we are going to do right click, insert layer below, signal. Now we have 4-layer stackup, and we would like to maybe rename the layers. So this is layer 1, layer 2, layer 3, layer 4, okay, and also adjust the thickness based on the stackup from JLC PCB website. 0.035 millimeter. Dielectricum is 0.0994. And watch, because we have the symmetrical stackup, also these changes are happening also on the other side of our PCB between layer 3 and layer 4. So that's why I kept the checkbox stack symmetry checked. So we don't have to, we only need to write it once. See? All the other numbers are correct. Now I'm going to uncheck this. And one of these layers I'm going to change from signal to plane. This is going to be our ground plane. Layer 3, big ground plane. Okay, so this is the stackup what we are going to use. Perfect. I can make Altium large. And don't forget to save the stackup. Change back to mills, press Q. And now you can see we have 4 layers. So save our board. I'm going to show the connections. And you can see all these ground pins we can simply connect to this layer 3. It's a plain layer. So go on this layer, double click, and set this layer 3 as ground. Watch what's going to happen, okay? Now these pins with vias are suddenly connected to this ground plane, and there is this kind of weird connection on this layer 3. Go to design rules. This is called thermal relief. So we need to adjust this thermal relief on plane connections to direct. Okay, so all the vias on layer 3, the ground vias, are going to be connected directly without the thermal relief. Okay, now I'm going to copy this via and the connection, and I'm going to paste it to all these other pins. And this is the simplest way how we can connect all the pins to ground. They are directly connected to the layer 3, and the layer 3 is ground plane. So basically everything what we need is just a via going out of the path to connect to ground. Almost done. Okay. Now what about this? There are still many ground pins. I'm going to hide the connections because I can very nicely see which are ground pins because they are blue. I'm going to hide the layer 3. We don't need to see this layer 3. We know it's just a plane. And I'm going to connect these. And notice I'm using a wider track. So when you are drawing the ground or power tracks, make them wider, 20 mils for example. Just press tab and you can change the width in the properties panel. I forgot to tell you this when I was drawing the very first ground and power connections. So be careful, okay? Make all the ground and power connections wider. I will place all these vias to these ground pins. And also I will place some vias into middle, like this. Place the vias on the path so they will pick up the net name. You can see inside of the vias it says ground. It means it is connected to ground. That's why I place them on the top of the path, because then they will be automatically picking up the net. If you place it into empty space, then the via will not be connected to ground automatically. Okay, be sure they are ground vias. And later we will draw a polygon there. We will connect them with ground copper. But for now it is okay. Let's continue here. Let's draw the connections. Maybe adjust the width. Maybe 20 was too much, so change it to 15. And place a via. We can connect also this one. Okay, and this one. Okay. Few more ground pins. This is power pin, so keep it wide, 15 mils. Doesn't want to go from the middle. Okay. If it doesn't want to route from the middle of the pad, you can just finish the connection and then just move the track. Sometimes it helps. Okay. Right now, draw these connections and add vias for every single power pad and ground pad. And later, when we will be finishing our PCB, when we will optimize the PCB, then we will draw some copper areas. I'm going to work only with tracks, and I'm going to change the width of these tracks because I forgot that they have default 10 mils, so I'm going to make them wider, 15 mils. Okay. Don't forget to switch off the filter and save everything. Still some ground and power pins are down here, unconnected. Okay. 20 mils. And connect this one here, this one here, okay. This one I can connect, make it 10 mil because this is standard signal, okay? So use 10 mils for standard signal. This is very important for all the standard signals. Use 10 mil tracks. A little bit later, when we will be finishing PCB, you will see why. Okay, save. Let's connect all these other. Or maybe before we connect them, we would like to place vias into this area. I already mentioned before you start drawing tracks in specific area, put all the vias there because then it will make your layout faster. You don't have to keep redrawing. You will simply just go around these vias when we will be drawing the tracks on the bottom layer. So connect all the power pins and ground pins to vias. A few more. This is the LED. Okay. Now this one, and this is the button ground. Okay. Save. And yeah, we can start connecting these signals on the bottom layer. Be sure you are using 10 mils because these are standard signals. And same as before, we need to route them very close to each other because there is not really much space. So do it exactly the same way as what I'm doing here. Very close to each other, like this. Okay. In case when you finish doing this routing and you find out you have more space, you can always make them wider, or you can spread these tracks. But if you are finishing the layout and you find out you have no more space, you will need to reroute everything. So it's much better just route everything as close as possible and then spread it, rather than route it somehow and then find out you have to reroute everything. Okay. I will move it a little bit. We need some space. Okay. Perfect. Connect it here. Make it nicer. Now you can see now there are these vias. So when we are doing this layout, we can very nicely go around the vias. And this is going to save us a lot of time. If the vias are not there, we would just route in that area, and then when we would need to place the vias there, we would have to reroute everything. I'm sure you understand. Or if not, you can try do not place the vias, and then you will understand what I'm talking about. Okay. Nice. Our board is filling up with tracks. It looks more and more professional. Okay. Make it nicer. When you are doing layout, then top and bottom layer is visible, so everyone can see your layout. So sometimes you would like to really make it look nice, even if from connection point of view, maybe it's not so important, but many people will see your board. If you can make it nicer and still working very well, then just make it nicer. Okay. I'm going to save it. Next, go on the top layer and we are going to have a look where this is connected. Here. Here. Okay. Okay. Let's try this one. Maybe from here. Go on bottom and continue. Next one is this one. Continue on bottom. At this stage, you can make the adjustment, make the layout nicer, but at this stage, do not spend too much time making your layout nicer, because very often you may need to reroute some tracks. You will be making these adjustments, or we will be making these adjustments and making PCB nicer by the end of the layout. Right now the main goal is to connect all the pins as simply, as quickly as possible, so we can see if we can make it, and also we can see where is possibly additional space which we can use to improve layout. Okay, next one. If you would like to learn more tricks and tips about how to design very complicated boards, don't forget, I already mentioned I created a number of online courses about PCB layout, schematic design, so have a look at FEDVEL.com. Okay, I have designed very complicated boards, motherboards, so this board what I'm doing right now is super simple. It's really fun actually to do this kind of super simple boards. Okay, I like it doing it this way because you almost see the results almost immediately. When you are building very complicated boards, it can take I don't know, 4 months until you know if your board is working or not. This simple board, you can just create it, I don't know, and get the board within 2-3 weeks. And also they are not very expensive to build, so if there is a mistake, you can very easily fix it, or you can just build the board. Even if you are not sure if it's if everything is going to work or not, you can just build the board, find out what is working, what is not, fix it on the board, and then just you know, send the updated board to production. It's one of the ways how you can design boards. The other one is make perfect design. First version will be working perfectly, everything will be working. Or do it quickly and then fix everything and redo it. Okay, maybe we can continue up here. So I'm going to connect also these other pins. When you are designing very complicated boards, you really would like to be sure everything is going to work, because it's super hard to debug complicated boards, and also it's very expensive to actually build them. So there are differences between designing different kind of boards. Connect this one. So here we just need a via, and we need to connect this. Okay. Okay. Perfect. Have a look where these pins are connected. They are connected together. This is the LED. And notice all the unnecessary objects are hidden from this PCB when I'm doing layout. The net connections are hidden, the overlay layers are hidden, because you really would like to focus, you really would like to see where the free space is, and you really would like to see how the tracks look, where the paths are. That's why they are all hidden. Don't forget, keep saving your board, just in case. these are connected here. Okay, so we can continue. Do it like this. Maybe I need to adjust this a little bit. To reroute, you can just go to routing mode and you can click on existing tracks, like what I'm doing right now, and it will automatically reroute it. See? Okay, maybe I need a little bit more space. Sometimes there are also features which can move multiple tracks all at once, but sometimes I don't use them because they can move some of the tracks which you don't want to move, and if the rerouting or redrawing is very quick, I just redraw it. Okay. Okay. Next one. ESP is almost connected. It's very quick. This is, as I said, this is very simple layout, so this is very quick. Keep thinking where you place the vias. Because as I said, we would like to have some space between the vias. Because for example, now on layer 3, around these vias there are holes. Yeah, so you don't want to have too many holes close to each other because they will break the ground plane. Okay. What else? This one. We can connect it. Go on the bottom. And just connect it. And also this one. Maybe like here. Okay. And we can connect the some of the pins around the FTDI chip. But first I will place the ground via here because it's getting close to the area where we need to route tracks. So I will put here a ground via. And also here. See, if we would be placing the via directly on the tracks, we would have to reroute the tracks, but we are lucky here. Here is a little bit of space, so we don't need to reroute anything. And also here is some space, so we don't need to reroute the tracks on the bottom. A lot of space for via. Okay. At the vias here, okay, to ground, and I'm going to reroute it. Maybe move it a little bit away from the via like this. Okay. And we need to place 3v3 here. Okay. What else? These are connected together, so we can place via here. See how I keep redrawing the tracks on the bottom because we didn't place the vias first. Good example. Why to place vias first. I need maybe a little bit of more space, make it nicer. Okay. Save everything. I'm just checking where these pins are connected. So these are the RX and TX pins, and we need to connect them to the ESP32. So, this is unusual. There is error. So we need to make an exception, because now suddenly there is a track to path violation, less than 10 mils. So what I'm going to do, or what we are going to do, we are going to create special rule, design, place this rule, which we need for the special rule. Name it FTDI, and notice what we are going to do. In design, rules, clearance, I'm going to create new rule which will only apply for this special area where the room is. So I'm going to use this custom query and write this within room FTDI. Clearance is going to be a little bit smaller. So what is the smallest one what we can use? Minimum spacing 3.5 mil. We don't need 3.5, we can use 6 mils. Okay. See, now the error is gone. Green color is gone. So it means in this FTDI area, we can now route with 6 mil clearance. We have no space here. Okay, I will place it like this. And also connect this TX signal. Or do fan out. This is called like fan out when you are drawing tracks going out of the paths and then they are connected to vias. So this is usually called fan out. And let's continue drawing these connections on the bottom layer. Place a via. Do it also for this other signal. place a via here, and then we will continue on the top layer. So these are one of the longest signals on our board, going also from one side, top of the board, to the bottom of the board, from the left to the right. Almost finished. These tracks are almost finished. It's going to be simple connection now. Just go down and make connection with the resistors, 0 ohm resistors. Okay, this one is done. And connect also this one. Perfect. Finish the routing of this RX and TX signal, make this short connection, and double check. Okay. 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 Press Ctrl and left click, okay, if you would like to highlight everything. Save. We are going to continue here around the USB to UART chip. So this is power. Use wider track and place a via. Okay. I need to make a little bit of space. Perfect. Go back on top. Now these ground pins. Very often if you make this kind of fan out and they are same on many components, you can just copy and paste them. It can save a little bit of time. Connect this. So this is the sense signal. Make it nicer. Maybe like this. Connect also this. This is a very simple connection, direct connection between the chip and the resistor. Okay, now the ground pins here. These are the decoupling capacitors. First, I'm going to connect the ground pin of the chip. I'm going to make it a little bit wider. Okay. Now, ground pin of the decoupling capacitor, the first one. Some people ask why we don't connect all the capacitors or all these ground pins which are close to each other, why we don't connect them together and then use one via. We place, as you can see, we connect each part individually and each of them has its own via. So it's better, okay, if you can, for power pins, ideally you would like to have one via per power pin. Sometimes it's not possible, then you can connect more power pins together. But if it is possible, then use one via per power pin. Make it a little bit wider. Okay, so connect the power. Okay. These are the decoupling capacitors, and these are the 0 ohm resistors. This one is connected to 5 volts. These are the reset pins or reset paths. I would like to see the components clearly. So this is the 100 nanofarad, and this one is the capacitor for the reset. Okay. So if you would like to identify the components, you can play with this overlay layer. You can select components in PCB, and they will be also selected in schematic, so you can very nicely find out which component is which. But because this is very simple schematic, you probably remember all the components. Okay, so this FTDI, this is a power, and we would like to have a wide and good connection, but we need to connect it to the other part or other side of the chip, so we need to use a via, and a little bit later we will figure out how we connect this bottom left corner of the chip with the top right corner of the chip, where the where this 3v3 FTDI continues. Make it wider and connect it. Okay. We can connect these ground pins. They are simple. Ideally, these connection, the power connection and ground connection to these power and ground paths, you would like to keep them short. These are USB signals, so we will route them a little bit later. But we can connect this capacitor. This is super simple to connect. Okay. And connect this. Perfect. We will route the USB signal a little bit later because we need to do a few settings before we start routing differential pairs. So first just finish these other pins. We need to connect also this middle path, or it's called exposed path. We need to connect it to ground, so place ground vias here. Okay. This is also connected together. So this is the second part of the 3v3 FTDI power. And I'm thinking how to make space, because we need space for the other pins. Maybe like this. Save. Now let's have a look what we need to connect. Many pins connected here. This is the power. Also we need to connect this one. Okay, so I'm going to hide it again, and let's connect this one. Be sure you are using the correct width, 10 mils. Go around the existing tracks, and maybe here we are going to change the layer. and continue on top layer. Okay. Small adjustment. What next? This and this. Maybe we can connect these. So we can connect this on top layer directly. Okay. And also here, this is a simple connection. Connect these pins. It looks really good. Now this. Small circuit which is helping us with the signals for programming. Ideally, we would like to connect everything on top layer. And because we created really good placement, it may be possible. Let's try it. Okay. Oops. Okay. And this one. Go down here and connect to transistor. These two together. Maybe like this. This is the button. Okay, and also here. Control left click into empty space to unhighlight everything. This one. So control left click because we would like to see where it is connected. And we can draw the connections. I will do it this way. Okay. Okay. And we have to connect it to the rest of the circuit. We need to connect it to ESP32. So let's do it this way. We still have a lot of space on the bottom layer. Oops. Oops. Okay, let's try a different way. Let's start from here. and connect it. Okay. Go on top layer. Save. What else? Differential pairs. But there are these ground paths in the way. So first I'm going to connect all these ground pins, and later we will route the differential pairs. So let's do it. And this big ground path, it's from the regulator. And the regulator may be getting warm or hot. So instead of only one via, what I'm going to do, I'm going to place there multiple vias. Okay, all this, we would like to cool it down. It is the regulator. Here, everywhere here, I would like to create a ground area, big ground area, which can help us to cool down the regulator. Place 4 vias on top of this big path, because then the vias are connected to ground, and move them like here. Oops. I'm going to use filter. I would like to only work with vias. Much better. Okay, so place the vias like this. And we are going to create the via array. So I'm going to select all the vias, press Shift, hold it down, and copy all these vias and paste them here. Oh, notice they are not connected to ground. So go back, and we are going to use this special paste. Check keep net name and watch. Now when I paste these vias, they are connected to ground. Very useful feature. Okay, one more row, and lock these vias, because there is a special feature in Altium, automatic loop removal, and log also this. And if you sometimes try to connect these vias, some of them may be automatically removed because they create loop, but when you lock them down, they will not be removed. Don't forget to turn off the filter, save our board, and let's have a look. What is this? This is the output connected to these two capacitors, and we would like to connect this ground to the ground of the capacitors. So I'm going to do it this way. This is a main power, so I'm going to use multiple vias for several reasons, but one of the main reasons why you would like to use multiple vias on power is there is a limited current which can flow through one via. So for power rails, you may need to count or calculate how many vias you need. There are useful calculators. For example, you can use free calculator. It's called Saturn PCB Toolkit. Very useful software which can help you to calculate all the kind of different values which you may need when you are doing PCB layout. Okay, Saturn PCB Toolkit, remember, or search for this software. I'm going to connect the decoupling capacitors and the output of the regulator. See, this is the automatic loop removal. Did you notice the track was automatically removed? Later we will put polygons there, but right now this is okay. I always keep saying later we will put the polygons or big coppers there. The reason is because when we are still doing layout, we need to create this special area also here because we are getting problems. So I'm going to draw a room. I will finish about the polygons a little bit later. So first I'm going to create this room. I'm going to call it USB-C2, and I'm going to adjust the rule which we used for the clearance. I'm going to add here this additional condition. So in this area we can use the 6 mil clearance. Okay, and I'm going to continue about the power plane. So right now I don't create these big copper areas because it's hard to see through them. I'm going to create same room also here on the second USB-C connector. And if you create too many power planes, too many copper pores, then it just makes the layout harder because, as I said, it's hard to see through them. So right now when we are connecting all the pins, I don't use the copper pores. We will do it when we will be finishing the layout. Okay, create the same rule also here. And let's continue connecting all these other pins. It's a little bit thinner, so instead of 15 I'm going to use 12. Okay, perfect. Connect also this one. If you don't know what is the copper pore or polygon, later you will see. But basically these are not tracks, but these are like bigger copper areas. We will use them for power, you will see later. First just connect this. Okay. Few more pins. And these components around these second USB connectors are almost connected. Place a via. Okay. Also here, make it a little bit thinner, 12 mils. Place a via. Save. And double check where everything is connected. Okay. So these are the USB signals. This is power from the USB. We can connect it. We would like to make it white, so I'm going to change the width to 20 and maybe connect it like this. Okay. Okay. Make it nicer. Oops. Oh. Okay, perfect. Later we will create polygon there, so for now just ignore it. Next, I'm thinking this, we can connect this. So these are the 5.1K resistors. if you would like to learn a little bit more about this USB-C connection and these resistors, then you can also have a look on my other tutorial where I was creating a very simple USB-C 5-volt power supply. But very simply to explain, these resistors specify what kind of current and voltage this USB-C connector can deliver. And now we are going to do something very special. We are going to learn about impedance. So search for standard digital track impedance, and you can see it says 50 ohms. What does it mean? It means all these tracks, standard tracks, should have 50 ohms. What is 50 ohms? Search for JLC PCB impedance calculator. 50 ohms is impedance. So go on this website and we are going to double check what is the track width on our board for 50 ohm impedance. So for our PCB stackup 3313, this is the stackup what we are using, okay? 3313. You can see this calculator is saying our track width should be 6 mils. I will double check if we can manufacture 6 mils. So minimum was 3.5, it's okay, we can manufacture 6 mils. And don't forget this number, okay? Later we will apply this, we will go back to this. But now search for USB to 0 impedance. And it says these tracks should have impedance, differential impedance 90 ohms. Go back to calculator, duplicate this, and we are going to have a look what kind of width and space we need to use for 90 ohm impedance. Space 6 will require 5.5 trace width. I will change the space to 8, and then trace width is 6 mils, okay, for 90 ohms for our PCB stackup. This is what we are going to use, 6 mil width and trace and the space 8 mils. So go to rules, and we are going to set up this differential pairs routing based on the numbers what we just calculated. These are the numbers what we need to change. So trace width 6 mils, trace space 8 mils. Minimum width 6.3, minimum gap 8, preferred 6.3, minimum 8. And I don't want to use exactly 6 because these are the tracks of differential pairs, and for our 50 ohm we will use 6 mils. A little bit later you will see why I didn't want to use 6 mils also for this differential pair, because we will do some filtering. And inside of the PCB we can specify also what kind of width and trace space we need to use, but we will not be routing this USB inside of our PCB. I will just fill up these numbers here to give you an example. So if you have more complicated board, you need to fill out also this specification for differential pair also on the inner layers, not only on top and bottom. I'm going to leave this uncoupled length here, 500 mils, and I'm going to apply this rule to our 90 ohm tracks. Save everything. So this is our USB. This is the this is the specification of our USB differential pairs, and here you can find all these differential pairs which is specified in the schematic. Okay, these are all the USB signals, differential pair USB signals. I'm going to use interactive differential pair routing and connect these. Okay, 10 mils. So let's have a look what the problem is. Minimum gap is 8 mils in our differential pair. So we need to make new rule I'm going to call it diff 90 clearance. And for these differential pairs, we will specify that they can have a little bit smaller clearance than the default 10 mils. So if something is in a differential pair class called diff 90, then it can have minimum clearance 8 mils. Okay, this should fix the problem. Okay, perfect. And I can make it a little bit nicer. Maybe like this. I will reroute it. Okay. Okay. I'm going to save this and maybe double check. So measure the distance between them. It's 8 mils. Okay, perfect. And what is the width? 6.23. Why it's 6.23? It's supposed to be 6.03. Let's delete this. Select one and then press tab. You can select all the other segments connected to the track. I'm going to try to route it again. Here, I'm going to set 6.03. Okay, now it looks it's routing correctly. 6.03. Okay, I'm going to make it nicer again. So when you try doing layout of this differential pair for very first time, double check, okay, if the size of the track is correct. Oops, go back, maybe delete this and try to connect it again. Okay, I just would like to make it a little bit nicer. Okay, okay, perfect. Delete this. Maybe not like this. I would like to work only with tracks and select this. Okay, delete. Perfect. Don't forget to switch off the filter. 603 and the gap between them 8. Perfect. Okay, so this is exactly how our differential pair should be routed. Now it should work when we continue. So save our board and let's connect this and this. I'm going to fan out these paths. So very short track going to via. And I'm going to copy this because for differential pairs we would like to have the connections, the tracks symmetrical. They should have same length. And let's draw this differential pair. Okay. Okay. Maybe like here, here. And when you use plus and minus, you can automatically insert vias. Okay? Plus and minus will change the layers. Maybe I would like to move it a little bit. So if you would like to move something, select it first and then move it. If you do not select it, if you just try to move it, then it will keep the connection and it will be moving the object also together with the connection. If you don't want to move it with connection, select it first and then move it. These are the default Altium settings. You can change them in preferences if you would like to use different behavior. but that's very good setting. No need to change it. Okay, and connect it on the top layer. So we routed our first differential pair on our board. It looks good, it looks nice. Okay, maybe small adjustment. Okay. No. Maybe like this. I like it. Okay. And don't forget to save your board. In these places where we are changing layers, we are going to put ground vias. And these vias are called stitching vias. And they are needed when signals are changing reference planes. Right now we don't have ground plane on layer 2, so right now they are not connecting the ground plane on layer 2 and layer 3, but later we will create the ground plane on layer 2. We need to do it also on this other side. And if you don't know exactly what the stitching vias means, why we need them, then have a look on my free YouTube videos. In some of them, or in a number of them, we are actually talking about this topic, why they are important, for what frequencies. You can see also some simulations where or when these stitching vias are used or when they are not used, how far away we may want to place them. Yeah, very interesting topic. I'm going to lock them down so we are sure they will not get moved or lost. And we are going to connect also these USB signals. I'm going to do fan out manually. I would like to have exactly same on the other side, so copy. And don't forget, use X and Y keys to mirror or flip. We are going to do fan out also on the other side of this USB. So I'm going to route USB signals down here, and then we will connect them on the bottom layer. Plus or minus go on the other layer. Vias are automatically placed, but I would like to move them a little bit. Maybe I will delete this and just place the via, and also this one. So select and then move it, and I would like to have them a little bit further from each other, maybe like this. Okay, now I can connect it. Perfect. Now go on bottom and connect these vias together. Okay. Down here. Perfect. Double check the width and space. Everything is okay. Shift C to hide the dimensions and save. We would like to draw the connection also here, but there is error. So let's have a look inside of the rules. What the problem is. This is the priority one, 8 mil, and the lower priority is 6 mils. So we need to actually swap the priorities. Select this, and okay, select this and increase priority. So first, highest priority is 6 mil, and then the second one is 8 mils. Let's have a look. Perfect. This is exactly what we needed. Sometimes these priorities are very important, okay? You need to be aware there are priorities in the rules. Now we can connect it. And as I mentioned before, when we were drawing schematic, this connection or this layout is not perfect because there are very short stubs which are connecting the first USB pair and the second USB pair on this connector. This is not like really proper way how to do differential pair layout, but for this board it is okay, and for USB it's okay, and it's very small. Okay, these stitching vias what we placed here, we don't need to place them close to the connector because there are already many ground vias, but we would like to place them here. So I'm going to do it. And stitching vias, they help with return currents. Okay, because each signal, it needs to have also return current. You know, even battery has plus and minus. Power supply has plus and minus. So currents flow between plus and minus. Watch the net. What is this? You can see it down in the toolbar. Okay, let's connect this second USB. Hide this. We would like to have nice and direct connection between these pins and the resistors. And doesn't look like nice. So I'm going to delete this. I will try to correct it somehow, make it nice. Delete. I have to delete also this. Okay. Let's try it. Perfect. Now delete this. And let's try it. Okay, maybe move it a little bit. Oh, okay. Okay. Perfect. Looks nice. Now, very difficult task. What do you think? What is difficult task? Watch. We need to swap. Here is P, and here is P, here is N, and here is N. We need to swap these pins. How we are going to do it? Do you know? We need to route on the bottom layer. So we need to place vias here. And going on the bottom layer will help us to swap the signals or the tracks. Very useful technique. I use it a lot. If you need to swap something, change layers. Okay. Doesn't look very nice. I will correct it. Okay. Ah, this is nicer. Delete this. Now copy and paste. Don't forget X and Y. Save. We are going to connect the connector to the ESD protection. So draw it very similar way as what we did on the other connector. We need to connect these two positive pins together. Make it nice, short. Important is make it short, small, so it doesn't influence the signal too much. We can connect this directly, then connect the second negative signal or negative path, and connect the positive signal. Okay. I will adjust this a little bit. I would like to have it very similar way as what we have there. It's tricky. Doesn't want to snap there. Okay. Let's make it this way. I don't want to work with grid. I switch off all the snapping points and I will just draw it like this. Okay. Put everything back. So cursor will snap to grid and snapping points. Save. And we are going to connect this on the bottom layer. So this way, notice we will swap the N and P signals together. Again, this is not the most optimal way to route signals, because one of them will be a little bit longer, the other one is a little bit shorter, because we are doing this very sharp turn. But for this USB, it's fine. Connect the ground pins. For some very high-speed signals, it's super important how you actually route these differential pairs. But for this USB, it's fine. It's not so super very high speed. Connect also these ground pins. And again, in this place, we don't have to put stitching vias, because you can see there are many ground vias anyway. So these are like stitching vias. Okay. Make it nice. Now, what next? Maybe we should finish this. So I'm going to continue and connect the rest of these ground pins. Place a via. Okay. Some of the people, they are talking about what is the right angle for tracks going out of the paths. Maybe you noticed in this design, most of the time I'm going out through the corner or directly. So there are no sharp corners. But I think these sharp corners in PCB layout are not problems anymore. But if it's possible, then you can do it exactly same way. Okay, don't use sharp angles in PCB layout. Sharp, it means less than 90 degrees. Okay. Connect also this one. Okay. Save. And power. We would like to use white track. Connect these together. And also the protection, jumper, and the capacitor. Connect it maybe like this. And we need to connect it also here. So I'm going to draw this connection on top layer and do it like this. Okay, I like it. This one, we need to connect this plus 5 volts. So zoom in, Control left click, so we can see what we need to connect together. We need a via, so I'm going to place one here. And we can connect it now. These through-hole pins are sometimes very useful when you need to change layers. So don't forget, if you have through-hole pins, then you don't need extra vias. You can use the through-hole pins. That's exactly what we are doing here. So we use the through-hole pin as a via. On the top, we will draw bigger polygon a little bit later. So don't worry about the thin track. And here I'm going to use very white track because it's main power, and make it a little bit nicer, maybe like this. Okay. I'm just thinking if we can do some improvements. Save it. This one, we still need to connect this. How are we going to do it? Ideally, we would like to connect it on the bottom layer, so we need to somehow move these tracks which are in the way. So I'm making space to reroute the tracks. Maybe like this. Could this help? We will see. Can we go around? Okay. And also this one is in the way. Okay, now we should be able to connect the FTDI power, but I don't like this. Can we improve it somehow? So this is the connection what we need, but I still keep thinking how to make it better. Okay, this looks okay. This looks good. We need more space here. So basically we are finishing layout, and this is what always happens. When you are finishing layout, you will start redrawing more and more connections because there will be less and less space. So if you are using, for example, auto router, or if you are just very new in layout, you will be like, oh, this layout is super simple, and first 98% is always super simple to connect, but the last 2% of your layout, that's what is difficult to connect. I still keep thinking how to make it nicer. I don't like this too much. Let's try it this way. Maybe move this via a little bit. Okay, now there is enough space. Okay, I like this more. I will just make it nicer, and this is what I will keep. Okay, because we are finishing layout, you can also keep making everything nicer. If you see something what you would like to improve, then you can move it. I'm moving this, for example, make the spaces same or bigger, or remove unnecessary bands. And we need to connect this. Because we moved the via, we still need to connect the top layer. Maybe like this. Here is problem. Less than 10 mils. Okay. Okay. Don't forget save. What else we still need to connect? This. This is the regulator and jumper together. Again, very important power, so we would like to make it wide. I'm going to make it wider. Doesn't want to. So go to rules, double check what the problem is. Maximum width, we need to change it to 100 mils on inner layers because it was 10 mils. That's why it didn't want to work. Make it wider and connect it. Okay. Okay. And only one more net left. .3 volts. Okay, let's connect this. We are almost finished with connecting all the pins. This is the last net what we need to connect. It doesn't mean a layout is going to be finished once we connect this one, but at least we know we can connect all the pins. You would be surprised. Some of the layouts are so difficult that until you connect the last pin, you are still not sure if you will be able to connect them, because I don't know, maybe there will not be enough space. Once I was working on a layout which when I was finishing, there was space only for the last via which I placed there, and that was it. Like no other space left. I was very lucky. And here few more things. So let's connect this here. And then down here, how we are going to connect this? Maybe we can connect it on top layer. So I'm going to rotate this. Oops, there is still track from 3.3 volt. We need to delete it. So work with tracks, select it and delete. And connect this. That's the LED. Sometimes it doesn't want to work the way as I would like to do it. Connect this. Okay. I need to make it smaller. No, let's move this. There should be enough space. No, no. There is not enough space. I will make it smaller, 20 mils. This is just LED and pull up. Okay. Make it nicer. And let's fix this one. Okay, it worked. This time it worked. I just keep thinking about how to, make bigger space between tracks. Okay. Save. Now go to design rule check. Here, change this to a big number, let's say 10,000. And we would like to enable all the rules. So in this batch, enable everything. And test points, we don't have test points, so uncheck this. And also signal integrity, we don't have anything set up for signal integrity, so uncheck all these. But we would like to run all the other check rules. Press this button and 517 errors. Unrouted net, this is important. Many of these we will fix them, and this is important. Net antenna, okay. This is the most important one, so let's have a look. Where is this problem? Ah, here. Okay. So just simply connect this path. And this one, which is this one. This means it only has one connection. And see, this is exactly the loop removal feature. See, I draw something and it will remove it on the other layer or the other track. But we should not worry about this too much. We fixed the unrouted net error, but there is still the antenna, because I told you, it removed the track on the other layer. For now, let's leave it as it is. We will place a polygon pore here, this polygon pore a little bit later, so it will fix the problem, it will fix the error. Everything else seems to be fine, all the nets are connected. So reset error markers and save our board. Next, we are going to check every single net on our board. So in this PCB panel, select nets, all nets. Be sure you have this set same way. Click on +3v3 and these are all the +3v3 nets on our board. Double check the width of the connection, okay? We would like to use wider than 10 mils for every single connection. Here we can maybe improve it. We can draw the polygon here because these are the decoupling capacitors. They are very close to each other. So let's draw polygon. Place polygon pore. Press G. Change the grid. Now left click and draw the polygon around these paths and vias. Polygon is the area which will be filled up with copper, and we will use polygons very often for some powers, like in this case. Finish the polygon. This is a little bit weird, but finish the polygon and we will adjust the shape later. When the polygon is selected, just move the edges, okay? Select it and assign the net. We would like to have this polygon connected to +3v3. Repore. This is very important, and there is still something wrong. Select it. The area is very small, so maybe uncheck this. Repore. Okay, there is something, but it's still not what we would like to have there. Go to Design Rules and double check this Polygon Connect Style. Select it. And again, it's using the relief, thermal relief. We would like to use direct connection. Now, again, we need to redraw it. So, repore. Still not perfect. We still need to find what is wrong. So, select it. And down here, select pour over all same net objects. That's what we need, this. Repore. Oh, finally, this is what we would like to have. These shapes are weird because it automatically would like to follow the clearance rules. So if there is not enough clearance, it will not pour the copper there. I would like to change the visibility. I would like to see the tracks. Maybe change it like this. I will move the track a little bit. These tracks right now, they are not really important, but I don't want to have it there because then I can't adjust these edges. Okay, now it looks good. Now it looks much better. Maybe adjust the visibility again. And I like it. I like this. Press Ctrl left click. Okay. Now, second net, this one. I'm going to save everything just in case. On the bottom of the first net, there is nothing on the bottom. On this one, we have something on bottom. First, check the top. Here we would like to again place polygon pour. So we can draw it around these paths and around the via. Okay. Don't forget to assign the net. Remove island and pour over all same net objects. Repour. Almost right. I can see when you select it. Oops. Select it. I would like to adjust the edges because I can see it doesn't follow the paths correctly. So change the grid. And also down here you can see there is the clearance 10 mils and it doesn't flow, the copper doesn't flow to the edge of the polygon. It's not important, but I always like to draw the polygons this way. I will move this a little bit further. Let's see if it helps to pour it until the edge. Okay, perfect. Perfect. I like it. We can save our board. And in settings, defaults, polygon, I'm going to change this. Okay, because we always have to keep changing this. So set it to pour over all same net objects. And next time it just should work automatically correctly. Polygon pour. Let's draw it also here. Around all the paths and the via. We don't want to draw the polygon under the chip because the size and shape of the path under the chip is very important, so I didn't draw the polygon there. Assign the net, repour, and adjust the edges. Okay, like this. I do it because, as I say, I would like to have full control over the areas where the copper is going to be filled up. And when I make these adjustments, I'm very sure it will always only be in the areas which I marked with this shape of the polygon. Press Ctrl, hold it down. You can actually add points and then adjust the shape a little bit more than just by dragging the edges. So if you would like to add this special point, don't forget press Ctrl and hold it down. Okay, Ctrl and hold it down and you can add another point into your polygon. Repour, move this little bit. Okay, I like it. Maybe small adjustment here. Like this. Select, select repour. Okay. Save. The next one is the 3v3 regulator. Here we are going to draw the polygon, which I mentioned a couple of times, that you don't have to worry about the net antenna error in this place. Draw it like this. Sometimes when you are drawing these tracks and polygons for powers, you may need to calculate if the track width is enough for currents. For high currents, I don't know, 10 amps, 20 amps, you can use again the Saturn PCB Toolkit calculator, the free software, to tell you, next plus 5e, to tell you if the width of the track is enough to carry the current. But in our board we don't really have any high currents, so we don't need to use like extra wide tracks. But very often, even for smaller currents, I just draw these polygons. It's nothing wrong to do. So this is the plus 5 volts. Okay, so this is the direct connection to the regulator, which is making 3.3 volts from 5 volts. Okay. Make it a little bit nicer. There are only few power nets left, so don't worry, we are not going to draw polygons for everything. Save. Next one, plus 5V VBus 1, top and bottom layers. Here we can create small polygon. Now you should be expert in drawing polygons. Draw the polygon, assign the net, repur, adjust if needed. Okay. Save. Also for the second USB connector, this one is a simple one, again just few lines. Some of the polygons are really tricky to draw, some of them are super simple. Okay, and also here, repur. And the last one, plus VCC FTDI, double check. Do we need to do something here? No. Okay, so this is just the button, chip PU. These are the USB signals. Ground. We need to double check the ground. We need to be sure all the connections are white So there is nothing on the bottom, but we are missing some polygons here. So first this one, I'm going to draw a polygon around these paths which are under ESP32 module. And then also we need a big one for our regulator, the one which is also used as a heatsink, cool down the regulator. So this one is finished. This one was super simple. Maybe small adjustments. Okay. Okay. Looks good. And now the regulator. Huge, big polygon, okay, for this regulator. We will connect all the vias and all the paths together with one big polygon. First, I will move this little bit so we have as much space as possible to create as big heatsink as possible. And all these vias which we place here will help to transfer heat to the big ground planes, which are going to be also on the layer 2 and which is also on layer 3. So it will help cooling down this regulator if it's needed, because the regulator can get really hot if we need a lot of current to take out. So we don't want to make it hot. Draw the polygon like this. This is a big one. More complicated than the one under ESP32. Almost finished. Okay, okay. Assign the net. And I'm going to adjust the shape a little bit. So again, press Ctrl, okay, hold it down. I'm just double checking if everything looks good. I like to work with bigger grid initially, because then it's easier to create nice horizontal and vertical lines, and then just change the grid to smaller one if we need to adjust something. Because if you would draw this big polygon in small grid, it may be difficult to create nice vertical and horizontal lines. Save. And continue. So GPIO 0, 1, 2. Okay, there is not really much to improve here. No polygons. This looks good. I always double check or I always check all the nets, even on very, very complicated boards with hundreds or thousands of nets. This is important one. This is the reset net, but we didn't name it. So what I'm going to do, I'm going to name this net. simply just place a net label and change it. And this is the way how you can make also changes in schematic and then put them inside of the PCB. So let's say I made a change in schematic, then you need to do update. This is okay. No, I don't want to change net color, so uncheck this. I don't want to remove rooms, and I don't want to add these nets or these supplied net voltages. Only this one is what I would like to import into our PCB. Don't forget to validate and execute the changes and double check. Okay, now it's called reset. Perfect. And it's here. So I'm going to continue. Where did we finish here? So double check rest of the nets. And they look okay. Everything looks fine. Perfect. Save. Now we would like to double check also layer 3. So make it active. Double click or just double check if it's connected to ground. Okay. All the green color, it means there is no copper, and all these vias, they are connected directly to copper. Also, these pins are connected directly to copper. Here, ground is flowing between the vias, so this is very good. That's why we didn't want to place vias too close to each other, because we would like to have them flow. And this is interesting. This is also interesting because it may be hard to solder these pins. So I'm going to adjust the thermal relief on this plane connect, and I'm going to use this advanced. For vias we will use direct connection, but for path connection we will use thermal relief like this. Maybe adjust the conductor width a little bit, make it 20, and watch what's going to happen. See? So right now these pins, through-hole pins, are connected through thermal relief. It means it's going to be easier to solder them down. Okay, save. Now disable layer 3 and let's go on layer 2. We would like to maybe draw polygon also here for the 3.3 volt power. First, I will adjust this a little bit. Now, place polygon pour and connect it to plus 3v3. Draw it this way. Okay, start from here and draw it around our 3.3 volt track. Do it exactly the same way as I do it, because watch what is on the top layer. This is very important to see tracks on the top layer, and we are drawing this polygon under some of these tracks. So these, for example, these GPIO tracks, they are routed above this 3.3 volt polygon. Okay, notice how I'm drawing the polygon, where exactly I'm drawing the polygon. Again, if you would like to learn more about these return currents and reference planes, you can have a look online on our online courses at FEDVEL.com, or also have a look on my YouTube videos. In my free YouTube videos, I explain a lot about these return currents. Okay, this looks good. I'm just double checking everything, or maybe make this a little bit smaller. And also here. Repur. Okay. Save. I'm going to make a polygon pur also here in this area where we keep getting the net antenna error. So when you draw a polygon is not going to disappear like tracks because the loop removal only applies to tracks. So now this will fix the antenna error. Okay. Save. And what left? Very big polygon connected to where? Ground. And we are going to draw it all around the board like this. Don't go exactly to the edges, draw it like this. And this is what happened. When you press F5, you can disable the colors. In Polygon Pur Manager, you can actually specify the priority. Be sure this ground plane is the last one. If you move it on the top, watch what's going to happen. When I repur everything, then there is only the ground pur, see? Because it has the highest priority. That's the first one which is drawn. But in our case, we don't want to have the ground polygon everywhere. It has to be, it needs to have the latest or lowest priority. Now when we redraw this, we will now have there the 3.3 volt polygon, which is drawn first, then also the other small 3.3 volt polygon, and then the ground big polygon. Very important, okay? There is priority how the polygons are created. I'm just double checking everything. I'm checking the return path for the tracks and the stitching vias. Maybe here we would like to place one stitching via because many tracks are changing reference planes, are going from top layer to the bottom layer. And the return currents for these tracks, they need to go from layer 2 to layer 3 or layer 3 to layer 3 to layer 2. So we would like to connect them together with ground via, with the stitching via. So that's what I'm doing now. Okay. Okay, this is good. I like it. If you are now worried like, oh, why he placed this via here? Don't worry. I told you, you can watch the YouTube videos to understand a little bit more why we are placing this via there. But if you don't place this via there, like, your board is still going to work. Then you may be asking like, so then why we place there these vias? Because sometimes they are very important for very high speed signals, but also they can help with EMC and EMI. That's why we are placing them. make small adjustments, like these are the final track improvements. Make them nice, spread them on your board. So if there is free space, spread the tracks so they are not close to each other, because there is something what is called crosstalk, and if you route signals very close to each other, then the noise can go from one track to the other one, and you don't want to have it this way. And when you put the tracks further from each other, then this crosstalk, this noise is much lower between different tracks. And have a look if or what tracks are crossing this gap. Ideally, none of them should be crossing this gap, but in our case we have some tracks crossing the gap. Again, this is connected with the return currents and some good techniques for PCB layout. You don't want to route over gaps, but if there is no other way, like in our case, and these signals which are crossing these planes, they are not like super important, so I'm not really worried, but I'm double checking what are the tracks which are crossing this gap between the planes, between the ground planes and the power planes. It's okay, everything looks okay. Let's improve this bottom layer. See, here we have a lot of space, so we can spread these tracks, make the gap a little bit wider, so there is lower crosstalk, lower noise between the tracks. Move it maybe a little bit more. Okay. I'm playing with it. Nice, I love it. It looks really, really good. I love it. Okay. Just double checking. Save the board. Press Shift S. You can change the views, single layer mode, and check each individual layer. And this is something maybe what you may want to double check. So it's the distance between the edge of the board and the power plane, and you can specify it here, okay, in the stackup. It's called pullback distance, 20 mils right now. Okay, so these are the openings around the paths and vias. That's this clearance, 20 mils. Okay. Layer 4, mechanical, we can ignore this, we don't use the mechanical, we don't use top assembly, we don't use top 3D, courtyard, we don't really use these layers, we don't need them for manufacturing. Top overlay, we need to improve this one. Bottom, top paste. This is important layer, so these are all the SMT paths where the solder needs to be applied. Okay. Top solder, these are the openings around the paths, and this is wrong. There is opening around the vias. We would like to have them tinted. We don't want to have opening around the via. So basically the green color of your PCB is, right now it is not applied on vias. We would like to put the green color over the vias. So I'm going to set it to manual and check as tented for all the vias in our board. They are now tented, and see, there is no opening in this top solder layer. And by default, we would like to have all the vias tented. So next time when we will be placing vias, they will be automatically tented. There will be the green color over them. See? Okay. Perfect. Drill guide. Okay, keyboard layer. We don't use this. This is the multi-layer. These are the through-hole parts or through-hole vias. Everything looks okay. Make the layer 1 active. Disable filter. Save our board. And we are going to add one more layer. Mechanical layer. Board shape. Okay. And on this layer, board shape layer, what we are going to do you know? We are simply going to draw the shape of our board. So I'm going to use 20 mil line. It's not really important how wide this line is going to be. And just draw it. When your PCB is manufactured, they need to know what is the shape of your PCB, so they will use this layer to cut out your PCBs. Save. And I will include this board shape layer and these other layers in the default layer set. Okay, these are all the layers which are important. Maybe I can disable this and save it as default. Save the board. Now we are going to improve this layer, silkscreen layer. Double click on this connector and it's J1. So place string on top overlay layer. It's going to be J1, and we need to double check the size. So go to JLC PCB manufacturing capabilities, 6 mil, 40 mils. Okay, that's correct. Move it maybe like somewhere here. Move it to the position which you like. I will leave it here. Now I'm going to copy it and paste. This is going to be J2 and it's the second header, it's the second connector. Save. Copy these two, paste them here. This one, the top one is going to be what? Do you remember? Go to schematic. It's the one which is connected to the USB to UART. So I'm going to name this one as UART. And this one, that's the second one. This one is connected directly to ESP module. So I'm simply going to call it ESP. Okay. Now, save everything. We would like to add also some description to this power selection jumper. VBus 1, VBus 2, and +5. So copy, paste, 1, 2, 3. Why we are doing this? Do you know why we are placing these descriptions on our board? To make it easier for everyone who doesn't have access to manual or maybe, you know, this board, it doesn't even have manual, it has only schematic. But when you are working with this board, maybe you don't always have your schematic open, and it's super useful to have the most important descriptions on your board, so you know what this jumper is about, for example. We will do exactly same also for the other one. So we are going to put some description here again. Then people can use your board without a manual, without documentation, without schematic. They just hold your board and they know immediately, okay, this jumper, when it is fitted, it will connect the regulator with 3.3 volts on your board. Okay, maybe it's not so clear, but if you know there is this kind of jumper, then you will know, oh, this is the jumper. Okay. Now, buttons. So copy, paste. We would like everyone to know which button is which one. I would like to know when I'm using these buttons. So this one is the user button or boot button. So I'm going to name it boot/user. And the other one is the reset button. This one. So reset, move it, and there is this pin number 1. We need to do something about this. It's connected with the footprint, so we have to double click on the footprint. We need to unlock it, and then when it is unlocked, find these primitives, unlock primitives, and it means you can work with the objects inside of the footprint when you unlock the primitives. Lock them again, lock the jumper again, and now the number 1 is gone. Okay, to delete the number 1, you just press delete button. User LEDs, user and power LED, we would like to name them. So everyone knows which one is user LED, which one is power LED. Let's select user LED, and it is this one. So I'm going to put here user, and this one, that's the second LED. It's going to be power. Okay. Save. Now we would like to mark these pins. I like to add small lines to these pins, because then it's very easy to find specific pin, like pin number 5. Okay, pin number 5 has this mark, and then pin number 10 will have another mark. So you can very quickly now find even pins like pin number 11 or 12 or 13. You just find the pin number 10 and you count 11, 12, 13. Okay. This is just something super useful, or something what I found useful if connectors, long connectors, if they have this kind of markers telling you or repeating every 5 pins, for example. I need to move this dot. So same technique as before, you need to unlock the primitives and then don't forget to lock them again. And do the markers also on this other header. By the way, if you update the footprints, which we changed, then all the changes will go back. That's why you would like to make all these updates by the end of your board design. Here is a violation, but we'll fix it later, and this is also a problem, so I would like to move this, or maybe delete it. We don't need it because this can't be really fitted other way around, so I just delete the pin number 1 marker. Okay. We are going to do improvement on the bottom layer now. We would like to add a description of these pins. So unlock this. I'm going to move pin number 1 away from the board. It's not important that it's away. During PC manufacturing, they don't really care if this pin is away. It just will not be on your board. Now I'm going to copy this text from the top of a line, and we would like to place it on the bottom. So place it on the bottom, and you have to mirror it. This is very, very important, okay? All the text on the bottom of your board has to be mirrored. Otherwise, you will not be able to read it. View, flip board. So this is the view from the bottom as you would see if you would hold your board. It's very useful when you work with text, for example. That's why I flip the board. And now you can see how it is going to look. You can nicely read the text when the board is flipped. So this pin is ground. And what we can do, we can now copy this and paste it also on the other pins. Okay. And as usual, we can copy more of these at once and then just do the paste of 5 of them at once, because it's just faster, like this. Okay. Almost done. Delete this one. And now, very hard part. We are going to name all these pins. You can see what this pin is about. Just have a look on the pin itself. There is the exact description of the net which is connected to this pin. And I will make the description a little bit shorter, yeah, because there is not much space on the board. And this is again super useful. So anyone without documentation, without schematic can use your board. They will know what is connected where just when they hold the board in their hands. It's a very quick way to check if you connect it, for example, a wire to the correct pin. GPIO 14, that's Slovak, GPIO 14. I made mistake. Sorry. You can guess English is not my first language. Okay, this is not connected. Perfect. We can do the second header. I'm going to place it here because this is the longer one. It has long description or long text. I would like to align it correctly. Maybe like this. Okay, remember the position. I'm going to copy and paste it. I use the one with long description because I'm aligning this text close to the header, so it will then look nice. Again, do multiple selection, press Shift, hold it down, left click and select multiple objects. And again, we are going to write description of all these pins. A lot of work. Just kidding. Our board is almost finished now. You have a lot of work already done. Okay. $45. Okay. I really hope you are working on your own board, and once you receive it and everything will be working perfectly fine, you will be very proud of your work. And I really hope making this tutorial help you a lot, because it is a lot of work to actually create this tutorial. It may not look like a lot of work, but I've been working on this tutorial for over half a year now. Okay, so thank you very much for still watching this tutorial, because it's super long. And actually, I started working on this tutorial 1 year ago, but then I didn't have time, so I just stopped working on it, and I started again half year ago from scratch, because there was new Altium version, so I wanted to use the latest Altium when I was recording. So I had to start again. Almost done. Okay, don't forget to save. Now, we would like to add more text. For example, what? Copyright, of course, copyright. We have to put there copyright. Put there your company name or your own name, so everyone knows you designed this board. Okay, what else we would like to have on our board? Maybe board name. I couldn't come up with any, so let's call it Have Fun version 1 issue 1. And save it. Next, what else we would like to have on our board? Do you know? Advertisement, of course. I would like to, tell everyone that we have online courses about hardware design, board design, signal integrity, EMC. Have a look at FEDVEL.com, okay? Don't forget. I know I keep mentioning this, but creating even this free YouTube video, it's not really free. As I said, it took me half a year, so I need to make money somehow, and this is how you will support when you signed up for one of our courses. This is the way how you support creating this free content. So thank you very much. Okay, save everything. Now, one more detail here I would like to mention, which is the pin number 1. So I'm going to use something like this. Okay, usually pin number 1 is also square, but not everyone knows that pin number 1 is square. So I would like to make it clear. Do it like this. This is the position, so I'm going to copy it and just paste it here. Okay, this looks good. Save. And the tools, design rule check. Be sure you still have all these checked. It's very important. You are checking for all these rules. And run design rule check again. Still 441 errors. Okay, we are going to fix them. This one, what is it? Power plane connect rule. There is problem with this. In panels, PCB rules and violations, we can see more details. So let's find it here in this list. Here it is. On layer 3, the problem is on layer 3. Block 3 out of 4 entries. I think I know what the problem is. This is the problem. There is basically only one connection. These three are not really connected because this color, it means there is no copper. So go to Layer Stack Manager, and what we are going to do on this plane, layer 3, we are going to maybe change this pullback distance to 0. Let's have a look if this helps. Save it, close this. Now notice there should, see, there is no like green color around the board, and now you can see there is the connection from 3 sides. So that's good. I think that should help. Let's try it again. Rerun. It's only 440 now. So we fixed this one. Cool. 440 go. Save our board. Don't worry, it's not going to be so difficult. Many of them, we will fix them very quickly. So what these are about. Mask clearance. Silk to solder mask clearance. Less than 10 mils between path and the track on top overlay. This is going to be a very easy fix because we just need to adjust the rule. This is the default rule from Altium. We didn't specify it. So everything what we need to do is double click here. This is the rule which is failing. So open the rule, and you can see basically the text or silkscreen is very close to the path. Go to JLC PCB, and we are going to double check how close we can place the legend. It looks like it doesn't really say anything. Maybe we can use something like this, 0.15 2 mils, 6 mils. Okay, maybe we can use this. 6. Okay, let's see if it helped. We can rerun design rule check. Sometimes you don't have to rerun design rule check, but it's always good to rerun it. Oh, 90 errors. This was good. Okay, 6. Silk to silk, 82, minimum solder. I'm going to save our board, and we are going to continue fixing the problems. So PCB rules and violations. There are many of these. So let's fix this one, minimum solder mask sliver. It's 6 mils, for example, here, and it's expecting to be at least 10 mils. So So it's basically this space between pins. Again, I'm going to double check in JLC PCB what is the minimum solder bridge. They call it solder bridge, or sometimes they call it sliver. 0.08. 0.08, that's 3.15 mil. And this one is like 6 mil. So in the rule, maybe we can change it to 3.15. That's, oh, no, we don't have to. Or you can use millimeters, actually. If you put there the units, see, it will automatically calculate to the mils. This is useful. I never mentioned this in this tutorial, but you can always use also the numbers with units, and Altium will automatically convert the units. You don't have to use the Google, which I always use. Now only few more errors. We are almost finished. These are a little bit tricky. That's why I left them at the end. So silk to silk clearance. This text is too close to the component. There is not really much about this kind of rule. I will simply just change it to for example this number. That's the 6 mils. I don't think it's like big issue for manufacturing. Otherwise they would list this in the manufacturing capabilities. And only what left is the silk to solder mask error. First, save our board and panels, PCB rules and violations. Let's have a look on details. Okay, can you see what the problem is? We are drawing the lines over the paths. So, how do we fix this? We need to unlock the primitives and simply delete this line. So select the track and delete this. Don't forget to lock the primitives again. Do it also for the second component. Unlock primitives, delete this track from the footprint. And this should fix the error. We have to do it for all of these. So I'm going to unlock all of them at once. I will delete all of these tracks, and then I will lock the primitives for all of these components. So what do you think? Are we going to have 0 errors now? I'm curious too. Okay, tools, design rule check, run design rule check. Yes, 0 errors. Well done. Save our board. And this is our finished board. I'm going to enable the components. Okay. Wow. I really hope you are proud of what you designed. Super cool. It looks so nice. I love it. You can see the LEDs, the green and red LED. You can see all the text, components. Super nice. There is one more thing what we would like to do. We would like to place here a very nice logo. So I'm going to show you how you can place picture. I created this picture. This is our logo, black and white picture. And what we are going to do, we are going to place it on top solder layer and place it like this. Okay, why top solder layer, do you know? Because it will be very nice. It will be gold logo on our board. Gold because there is copper in the place where I'm putting this logo. There is the heatsink area, so there is copper. And then when we will be manufacturing this board, I will ask them to use the gold surface. You will see it also in 3D view, so I will just move it like this. Be careful about the vias, because vias can disturb your picture. And in 3D view you can see this is very nice gold logo. Love it. I love it. It's very good trick if you would like to place gold text or gold logo on your board. Do it this way. Safe. Now, do you remember I mentioned the standard digital tracks should have 50 ohm impedance? So we need to adjust the width of our tracks. Right now they are 10 mils, but to get 50 ohm impedance from them, we need to change the width to 6 mils. How we are going to do it? We are going to use filter. I'm going to show you how you can create your own filters. It's a very useful trick. So I save the board. Now go to this PCB filter, top and bottom layer. I'm going to hide these overlay layers. Select a track and use this, find similar objects. Now same, so we would like to work with tracks, and tracks with 10 mil width on layer 4. And this is important. Create expression. Watch here what will happen. Okay, now it created this special expression, and we can modify it because we would like to select not only tracks on bottom layer but also the tracks on top layer. So I'm going to copy this and we are going to modify this filter. I'm going to put here or top layer, so layer 1, and now try to modify this, try to apply this filter. So select, deselect mask, apply to all, and now we have selected all the 10 mil tracks in our board. These are all the digital tracks which need to be routed by 50 ohm impedance, and they need to have 6 mil width. So you can change it very simply to this 6 mils. All these selected tracks, now they are 6 mils. Everything is green, all the errors. We simply just adjust this minimum width rule, change it to 6, press OK. Ah, perfect. No errors anymore. Clear the filter. You can use also this clear button in PCB panel, and that's it. This is the last thing what I usually do when I'm finishing PCB layout. Double check if everything is okay, if all the tracks were correctly changed. Double check the USB differential pairs if they have correct width. Have a look on all the digital, standard digital tracks. This one is wrong. I think by mistake I routed this different width, not, oh yeah, you can see 10.01. That's why it didn't change. Okay, so correct this. This was my mistake when I was doing layout. They is supposed to be 10 mils. Save again and rerun the design rule check. Done. Our board is basically finished. Save it. Go to projects and then output job file. This file is needed to create manufacturing outputs, or it will help us to create manufacturing outputs. Be sure you are going to save it inside of our directory. Save our project. And we don't have any variants of our board, so we are going to create one. Go to project, variant. Variant, it is something what will specify what kind of components we are going to fit. So for our prototype, we would like to only create specific components. We will see they're here. Okay. Now you can see in variants we have the prototype. Click here, this is very important. Select prototype because we would like to work with this. And we are going to unfit the components which are not fitted for making the prototype. These are the components which we mark with the NF text. Why we are doing this? We are doing this because these components, what we are selecting right now, they will be automatically excluded, for example, from bill of material when we will be building the prototype. Or we can see, for example, in schematic, which of them are not fitted. Or even in PCB, we will see some markers. You will see a little bit later how this is useful. Let's go back to variants and now have a look. See, it says for prototype these components are not fitted. You can change drawing style. So this is how in schematic we can see the unfitted components in schematic, but you can set also, or you can change some setting for PCB. So I'm going to select this and I will make few adjustments. So when we will print documents about our PCB, I would like the components look like this. Okay. Go here on the editor tab, very important. Save everything. Go back to our job file. Now select prototype. And it's because we would like to generate a manufacturing output for prototypes. And first we are going to create this. Refresh. So this is the top and bottom view of what we are going to create of our board. And do it exactly the same way what I'm doing here, okay? Change it to 50 and then change it back to 100. I don't know why, but this is only the way I found to refresh this page correctly. We would like to use the real size because we would like to print this board in real size on our on paper and do some measurements and compare with real components, so we are sure everything is going to fit correctly. That's why I would like to print this. Okay, these are the layers what we need. Perfect. And we would like to use like normal colors. Show holes. This is sometimes useful if you would like to double check also the holes, or if you would like to make the holes inside into paper. I'm going to add another page. This is going to be bottom side or bottom layer of our board, and we will do something very similar. We don't have any components on the bottom layer, but maybe we would like to double check the text. And use exactly same settings what I have here. Mirror layers, okay, don't forget. And This looks okay. This looks good. I'm just double checking everything. Okay. Save. Now I don't want to use this default PDF because I have problems with printing in the real size. So I'm going to add this Microsoft Print PDF. I don't know why, but many times I tried to print into the default PDF and I was never able to find out how to print in real size. That's why I'm using this kind of external PDF. And here is the file. This is how it looks. Okay, it looks good. See, these components are not fitted, so there is this gray cross which we specified when we were adjusting the drawing style of unfitted components, and print it in the real size. Okay, be sure you print in the real size, and then this is how it should look when you print it. Double check the sizes. You can also try to fit there the components or headers. Next, we are going to generate the Gerber files. These are the most important files to manufacture PCB. Our board is in inches, so I use inches. These are all the layers what we would like to generate, and double check them. Maybe we would like to also generate the board shape layer. Okay. There is one more file what is needed to manufacture PCB. It is a drilling file. So this file specifies the position and size of the holes. Use exactly same settings what I use. Save. And to generate these files, we are going to select this and then generate. Generate it one more time because there is some kind of bug in Altium forever, and when you generate it for very first time, it will generate it into these free documents, but we would like to have it inside of this output directory for our project. Okay, so generate it twice. You only need to generate it twice for very first time. It's a bug, I don't know why. To check these files to be generated, I'm going to use this ViewMate. It is a free software. You can download it and install it. When you open it, this is how it looks. I'm going to import the Gerber files from our project output. And I'm going to select all these files starting with G. Extension is starting with G. And I switch off all the layers, and by one you can double check the layers. Just double click to show and double click to hide the layer. You can combine these layers. This is super useful. For example, if you would like to see this mask or solder paste, you can very easily double check if there are no errors when you combine the layers together. If you don't see them correctly, you can change the color. Some combinations of the colors are better. Okay, this is a very good combination. See, there are the paths, and there is the solder, there is the solder mask or solder paste. Very nice tool to compare these. Okay, these are the inner layers. This is the outline. Maybe there are two of them, so maybe we don't need to generate the one which we created because one is automatically included in the outputs from Altium. And there is no paste on the bottom because there are no components, so we don't need to generate it. Okay. You can guess what are these layers. So GBL, Gerber bottom layer, okay. BO, bottom overlay. BP, bottom paste. BS, bottom solder, okay. I'm going to change the color so I can see better the combination of these layers, okay. This is the layer 2. And here is something wrong. We need to double check. What is this? Why the clearance is smaller in this area? Let's measure it. 6 mils. Oh, I think I know. Because of the special rule which we created in the room. So I'm going to save our board and we are going to make some changes. See, this is the room and exactly in the area there is the problem. So I'm going to apply the special rule only on layer 1. 6 mil rule only on layer 1. So I'm going to modify this rule. Only use 6 mils on top layer. Okay, now we have to generate or regenerate the polygons again. And there is still one small error. We need to move this via a little bit of the track. Okay. Refresh. Okay, now this looks good, but this looks like a problem. This piece of copper here. So select and remove that copper. Watch what's going to happen. See, the copper which is not connected was automatically removed. You don't want to have like unconnected pieces of copper on your board because they can make problems. Okay, we need to rerun the design rule check just to be sure we didn't make any mistakes. Now save the board. And I still like this board shape. So what I'm going to do, I will rather use our board shape and I will uncheck this automatically generated board shape by Altium because I don't know exactly how they create it. Close ViewMate, delete the old files just to be sure you don't send wrong files to production, and generate this again. Generate new Gerber files and NC drill files. Okay, I'm going to copy this path and go back to ViewMate. Go inside of our project directory, select all the files starting the extension with G, switch off all the layers and double check combinations of layers again. This is something what you need to get used to. Very often the very first files for manufacturing which you generate are not the right. Okay, it was fixed. So you need to get used to regenerating these files. Select this empty layer, layer 11, and I'm going to import the drill files. We would like to see if this drilling is also correct. So these layers include or show the information about the drilling, the position and hole size. It looks okay, it looks good. I will change the colors. Okay, this looks good. Perfect. Save. Next, we are going to generate the assembly output. So this is a pick and place file, which is needed for the machines which are going to fit the components. Use exactly same settings as I use here. Okay. Okay. Save. Now generate the file. And we can have a look what is inside. So I will make this wider. Oops, maybe move it like this. So in this file you can see all the components with the position and some other information which is needed to fit these components on your board. Okay. Perfect. Save. Next, bill of material. So this is the file what you will need to summarize all the components on your board. I'm going to remove this and I'm going to group the list. Watch what's going to happen. Right now the quantity is 1. I'm going to group them based on libref. So now the list only shows component types and then the quantity of each of the component type what we need. We need to buy them, for example, or you will upload this BOM when we will be ordering assembly service from JLC PCB. You will see a little bit later. Use exactly same settings. Save. And we can have a look what is inside of this file. So generate it. When you open it, it looks like this. All the components on our board. And they are here inside, or the file is inside of our project directory. Go to JLC PCB. Be sure you are logged in. And we need to upload a zip file. So what I'm going to do, I'm going to pack. I'm going to create new directory, so send to production, and I'm going to pack all these Gerber files. Okay. And also we need to add the drilling files. So I will copy them inside of the zip file. So this is the file what we need to upload here on JLC PCB website. In our project directory you can see I'm going to upload the file. Let's see what will happen. Okay, so this is our board. Now, down here we need to specify what we would like to build. Use exactly same settings what I'm going to use. Or if you like, you can change color or something. This is important, ENIC. So this is the gold on the top of our board. If you would like to have gold logo, that's why I use ENIC. And also we have very specific layer sequence. So we would like to be sure they build these layers, they build the PCB layers in the order how we design our PCB, because we would like to have the layer 3 the ground plane just above the tracks on the bottom layer. So select the layer sequence as specified in our board. Do it this way. Okay, confirm. Impedance control, yes. 3313, that's the PCB stackup what we used. This will help us to, have the tracks 50 ohms and 90 ohms. Remove order number. I don't want to have the number on our PCB. It looks ugly. Okay. Now PCB assembly, because you like to feed also the components. And you don't have to do it in JLC PCB, but I do it because I would like to show you how you can do it if you would like to do it. Because sometimes this PCB assembly can be expensive, especially if you have only very few boards, you can just solder them manually. Okay, next. Here is the place where we need to upload the bill of material and pick and place file. So find the files. This is the bill of material. And this is the pick and place. But before I upload this, maybe we would like to double check them. I will edit the name so it's a little bit easier. So open the BOM, and we don't want to fit these headers, so I'm going to delete them from BOM, and we don't want to fit these jumpers and links. Delete, save, and also double check pick and place. And we don't want to JLC PCB fit the through-hole components because they just cost extra money. So I'm removing them. And of course the links, they are not real components on the board, so that's why I remove them. Okay, save it. So pick and place and bill of material files are ready. Now we can upload them. And let's see what will happen. This is always moment of surprise how many components they have. Not bad, not bad. Only 3 components are missing. So double check what they have and especially what they don't have. So this is the ESD protection, and then USB and the regulator. That's okay, we can fit this manually. So don't place these components what they don't have. You can see the USB connectors are not fitted. And also the regulator is not fitted because they don't have them. Double check everything else. Don't worry about the specific rotation. From my experience, they will correct this rotation, and then before they send the board into production, you will receive an email and you will confirm the position. Okay, double check the prices. So PCB itself is not expensive. The assembly is quite expensive because you need to pay also for the components, and there is also setup fee, $25, you can see. Okay, assembly only the top side. This is the PCB. If you like, you can double check the Gerber files. Okay. Okay. And also you can double check the layers. So this is the final checking before sending our board into production. everything looks okay. This is negative layer. It means where the color is, there is no copper. Usually where the color is, there is copper. But if you go inside of these Gerber files, you will see it says negative layer. If you go to standard layers, like this top layer, it says positive layer. And the layer 3 is negative because we used plane in Altium. Usually when you use plane in Altium, the layer is negative. Okay, everything looks okay. You can also double check all the settings. Be sure your settings are same, or if you make adjustments, be sure your adjustments are correct. And this is the assembly. These are all the components, what they are going to fit. These are the components which are missing or which they are not going to fit. And this is the placement. As I said, you can ignore this rotation right now. They will have a look on this data and they will send you email, and you will confirm then the email what they will send you. Okay, we can pay. Let's see what will happen. I'm just going to use all these default settings. If you like, you can play with the delivery. Sometimes you can get cheaper delivery, especially if you are ordering only PCB. There are really cheap options to deliver PCB. Okay, so it's done. Now we still need to order the missing components. So I will buy them here on Farnell. You can use your own local component supplier. What is missing? What kind of components we need to buy and then solder manually. USB connectors, I'm going to copy part number and I'm going to find them in Farnell. They have them in stock and I can buy them in one piece. Minimum quantity 1 piece. We need 2 for 5 boards. That means we need 10 pieces. Okay, next one. This is the ESD protection. So let's find them. Do they have it? Looks like they should have it. It was listed there. Okay. And also they have it in stock. Perfect. Click here. How many we need? 6 per board. So we need 30 for 5 boards. Or if you like, you can buy a little bit more, just in case there is problem during soldering. But I'm not planning really to fit all the 5 boards, so it's okay. I don't need more. And this is the regulator. 1 piece for 5 boards, 5 pieces. Okay. And what else do we need? Do you remember? Because we removed some of the components before uploading to JLC PCB. So these are the 2 headers. I'm not going to fit them, so I'm not going to buy them. But we will need these jumpers, the header for the jumpers. This is the first one. Should be this one. Minimum quantity 10 pieces, okay. And also we need this second one. 2-pin header. They have it. Okay, 10 pieces again, that's the minimum quantity what we can buy. And also we need the cap for these jumpers. Okay, buy. What else? Everything else is okay. So this is everything what we need to buy. Go to our basket and buy this component. So in your case, it may be a little bit different. Maybe they had or didn't have in JLC PCB different components. Just buy the missing components, order them, so you have these components before your board will arrive from JLC PCB. Okay. Completely save the project, close it, and what I'm going to do, or what I did, I uploaded this project to GitHub. So go to our FEDVEL GitHub and search for ESP32 with USB-C. And here you can find the complete project from this tutorial. You can download it, download the zip file, and if you need, you can just open this project and use it. So the next day I received the email to confirm the placement. As I already mentioned, they will send you this email. They will correct the rotation and position of the components, and they will send you this email so you can double check, especially pin number 1 location. So I'm going to have a look on this corrected placement. Zoom in, and you can see now pin 1 is rotated correctly. These transistors are rotated correctly. So double check also the unfitted components. Everything looks fine. Okay, so we can confirm this placement, and our board is in production. If you like, you can also double check the data which they use for manufacturing your PCB. You can download them here. This may be very interesting because actually your board is going to look a little bit different. You will see I'm going to open these Gerber files which they use because they will add some extra things around your PCB. Unpack. I'm going to copy the path, and I'm going to open the ViewMate and import the Gerber files which are used for the production of our board. And let's have a look. See, the board looks a little bit different, and they need this extra space because this board will go into assembly machine, and it means you know, you can't put into assembly machine just the board because they need to hold it somehow, and there are these rails which are used to hold the PCB, so that's why there is this extra space needed. You can also double check the layer 3, and you can see that here it is. This is the layer 2, sorry, and this is the layer 3. See, now it's not negative, now it's positive layer, so it's full of copper. These are the holes. Okay, perfect. So this can be useful sometimes to see the real manufacturing data. And now just wait for our boards. This is what is happening in JLC PCB. See, this is the board what we designed. They placed it into this big PCB panel with other projects, and this is this PCB has not been finished yet. You see only the mask is applied. They still need to apply the silkscreen. If you would like to see more, I created a factory tour, JLCPC factory tour watch it on my YouTube channel. And this is how the board is assembled. Okay, so this is big machines with all the components, all the kind of components, and this is how the components are fitted on our board. They have actually two machines in a row, so these are the smaller components, and then from this is actually real time. From this machine it will be moved to the second one when the bigger components will be placed. This is the second one, and here are the bigger components. The ESP32 module, for example, is placed here. See how quick they actually place the components? As I said, this was real time. And have a look, they are placed here. And then of course it has to go to oven and checking and all the kind of things. But as I said, if you would like to see full video, it's on my YouTube channel. And here it is. I received the package from JLCPCB, and here are our boards. I'm very curious. Let's have a look. Open this. Very well packed. We need to somehow get our boards from this. I'm going to try my best. Okay, I can see the boards. And here they are. Okay, the first one, second one, third one, 4, 5. Now the components what we ordered from Farnell. And we should have everything to be able to build our board. Double check. USB connectors, pin header, 3 position, jumper, header, diode, this is the protection, and this is the regulator. Looks nice. Some of the components are not fitted, you can see it. Cool. Okay, double check everything, right? So these are not fitted. Also, this is not fitted, not fitted. Double check pin number 1 position, LED rotation. These are fitted correctly. Okay, okay. This is nice logo what we created. Regulator is missing, and the connector and protection. Double check the quality of soldering, and also double check if there are no short circuits between the pins. Because you really don't want to spend a lot of time trying to find out why your board is not working, and then you just have a look on your board and you are like, oh, this component is fitted the wrong way, yeah? Or this pin is not soldered properly. So double check everything before we connect the boards. This is called optical inspection. And it's very standard procedure to check the boards when you receive them from production. Everything looks okay. The last thing to double check, soldering under ESP32. Okay. Now I'm going to use this flux, and we are going to solder down the ESD protection. This component is a little bit tricky we need to use hot air gun. So first I will put a little bit of solder on these pads, and I'm using leaded solder. So if you can use leaded solder, because for this kind of boards it's easier to work with. Of course, if you can't use leaded solder, then use the lead-free one. I'm cleaning the board. Now I will place my board on these nuts. So when I will be heating up the board, the heat doesn't go away. Put little bit of flux and place the components. This ESD protection is not critical to make your board work. So if you are a little bit worried that you can't solder down these components, I'm going to heat up. Watch what's going to happen. If you are not very comfortable soldering down these components, you don't need to feed them. Your board still will work. Okay, this is just, for protection. And also I wanted to show you one way how you can solder down this kind of components. This is the flux what I'm using, in case you would like to use the same. We are going to solder down the USB connectors. This is the solder what I'm using, that's the leaded one. Again, I'm going to put a little bit of tin on all the pads, because you can see it may be a little bit hard to solder directly on the gold, and you can remove this excessive solder with this copper wire. I forgot how exactly it is called in English. This is what I use for cleaning. And also I use alcohol. So after cleaning the flux away, I will also clean it with alcohol. We don't want to have too many chemicals under the components. That's why I clean it. Now, put down the header. You noticed I placed a little bit more solder on one pin only. And once it is fitted correctly, then we can solder the rest of the pins. If you only put tin on one of the pins, then in case there is something wrong, you can always heat it up and correct the position of the component. But once you solder all the pins, then it's not going to be so easy to correct the position. Okay, so first, always when you are soldering components, first only put tin or solder on one of the pins, place the component, double check the position, and only then continue soldering the other pins, only if you are happy with the position. So I'm soldering the rest of the pins. And once you are finished with these pins, also solder down the shields. Notice how the solder goes inside of these holes. So I'm putting the solder there until it goes down. Make it nicer also from the other side. And double check if there are no shorts, and double check the quality of the soldering. Now the regulator, again, put little bit of solder on each pad, because it's hard to solder on the gold directly. Put solder on one of the pins. Now fix the component into right position, and once you are happy, solder down all the other pins once you are happy with the position of the component. Okay, looks good. Now the jumpers. So fit the cap. It will help to take heat away from the pins, and also it will hold the pins in place. If you don't fit the cap, the pins may heat up too much, and they will, kind of loose position inside of the plastic. Okay, solder it. Double check how it looks. If you are not happy, you can heat it up again and watch if the solder goes inside of the hole. Now the 3-pin header, same as before, put there the cap and finish soldering the pins. Okay, if you are using lead-free solder, then as I said, behavior of this melted solder is going to be a little bit different. Clean it, double check, looks good. Now remove these extra parts of PCB. These are the parts which they needed to assemble the board. You could see it from the video from the factory, how they used them or why they needed them. Fit the jumpers. Don't forget to fit the jumpers. Okay, this is how the finished board looks. Now, double check if there is no direct short circuit between ground and powers, between ground and 5 volt and 3.3 volt, and also swap the probes. So now I'm putting the red one on ground and the black one on 5 volts and 3.3 volts. Okay, there is no direct short circuit. That's good. And we are going to measure the current. So I'm going to connect this USB and watch what is going to be the current flowing, and also watch the LED if it's going to light up. Okay, it's green LED and 20 milliamps. Perfect. This looks good. And also try the other one and measure the current and watch the green LED. 70 milliamps. Perfect. So if there is something wrong, the current may go much higher, I don't know, 100 milliamps or more. 20 milliamps is perfect. Don't forget to fit the jumper again. Both of them needs to be fitted. And we are going to double check the voltages. Watch the LED, it should go green, okay? And measure first 3.3 volts. Okay, perfect. And also 5 volts. Cool. Now, search for Arduino, go on their website, software, download Arduino IDE. I'm using Windows, so I will download this one. Install it. Once you open it, this is how it looks. And go on this website. Okay, scroll down. There are some important instructions how to start this. Add board manager entry. So go inside this file, preferences, and copy there this line. I already have it there. Press OK, but I will cancel because I have it there. And then go to this tools, board manager, and search for ESP32. You need to have these expressive systems installed. I already have it installed. If you don't have it, then install it. And then you should be able to see here ESP32, and we are going to use this ESP32 S3 dev module. Go to Device Manager, and we are going to double check if our PC can see the board. Be sure jumpers are connected and plug in the cable. Okay, so in these ports you should see new COM port. COM port 21, that's where my board is connected. Here search for ESP32 S3 and This is what we are going to use, connected to COM21. Okay. And if you have problems with detecting the board, then search for FTDI drivers and install them. I already installed these drivers, so I was not doing it, but here are the drivers for Windows. If you use different operating system, download them. That's the chip what we use. Close this, just be sure everything is restarted and starting from scratch. This is the FTDI chip, that's why we install the FTDI drivers. Start the Arduino IDE again and go to these examples, basics, blink. We can close this one, and this is important, okay? Most Arduinos have onboard LED connected to different pins, LED built in. In our case, our user LED is connected to GPIO2, so we need to update the code. Here I'm going to add this. It means our user LED is connected to GPIO2, and I'm going to use this user LED also down here. And I'm very curious. Be sure you select the right board here and the correct port. Okay. Be sure your board is connected and press this button. Watch the user LED. What's going to happen? It should start blinking. Yes! Cool! Our board is working. Let's try more complicated example. This one, Wi-Fi, simple Wi-Fi server. We can close the blinky example. Here, set your Wi-Fi password, and we need to update these few numbers. So this is where we specify where our user LED is connected, and also swap these two because we have it connected a little bit different way. Okay, be sure board is connected. Open serial monitor and press this button. This is a very cool example. Do you know what this example is doing? You will see. So in serial monitor, you will see some outputs, okay? Be sure you are using correct baud rate. This is saying that our board is connected to this Wi-Fi net, and this is the IP address. So copy this IP address, go to browser. I'm going to paste the IP address here, and watch our board. Watch the LED on our board. Switch it off and switch it on. So through website, you can control the user LED on our board. Super cool. I'm going to use again the blinky or blink example. We can close this, and I'm going to directly just put here number 2. And what we are going to do, we are going to use the second USB port. So I'm going to plug the USB cable to the second port, and also don't forget to switch the jumper and watch what's going to happen. So first we should see the board on different COM port. Be sure you select the board correctly, and also the new COM port is selected here. Okay, and compile and upload. Perfect. Again, it works also with the second USB port. Cool. And that's it. That's everything for this tutorial. Phew. 8 hours. I have never posted so long video on YouTube. 8 hours is a lot of work. So I really hope you design and build your own board, and if yes, fantastic job. Well done. Now, you know everything important to start designing your own projects. If you would like to learn more about electronics, don't forget to check out what our online courses at FEDVEL.com, or you can have a look on my free YouTube videos. I have created many super useful YouTube videos. They can help you a lot to design better boards. So have a look, okay? My YouTube channel, Robert Feranek. Please leave your comments and let me know if you like this tutorial. Thank you very much for watching and see you next time. Bye.